तो ये एक बाइलिंगुअल सेशन होगा जिसमें हम ESE के PYQ डिस्कस करेंगे फ्रॉम द सब्जेक्ट कम्युनिकेशन सिस्टम्स। तो जल्दी से एक बार कनेक्ट हो जाइए और चेक कर लीजिए कि आपको मेरी ऑडियो वीडियो सारी चीज़ें क्लियर हैं। ओके, तो मेरे अकॉर्डिंग यहाँ पर ऑडियो वीडियो सब कुछ ठीक है, तो चलिए स्टार्ट करते हैं सेशन को। तो स्टार्ट करने से पहले आपके साथ जस्ट एक इन्फॉर्मेशन शेयर कर लूँ कि यहाँ पर आप एग्ज़ाम दोस्त पर आपके लिए सभी तरह के बैचेस अवेलेबल हैं फॉर गेट एंड ESE। तो अगर आप EE के एस्पिरेंट हैं और अगर आप 2026 या 27 के लिए गेट की प्रिपरेशन करना चाहते हैं फ्रॉम EE ब्रांच, तो यहाँ पर कोड EB30 यूज़ करके अभी आप ज्वाइन कर सकते हैं 2026 के लिए जो गेट कोर्स है ओनली एट ₹16,800 प्लस GST। और 2027 के लिए कोर्स जिसकी 2 इयर्स वैलिडिटी होगी वो आप ज्वाइन कर सकते हो ओनली एट ₹26,600 प्लस GST में। इसके साथ अगर आप देखें तो ESE प्लस गेट के लिए बैच अगर ज्वाइन करना चाहते हैं तो लाइव प्लस रिकॉर्डेड बैच अवेलेबल है ओनली एट ₹18,200 प्लस GST। और अगर आप रिकॉर्डेड बस चाहते हैं तो 10,500 प्लस GST में आप अवेल कर सकते हैं कोर्स को। वो आपको कोड यूज़ करना है EB30। ठीक है, तो एक बार कनेक्ट हो जाएंगे सभी लोग और बता देंगे आप सब लोग कि ESE के लिए कैसे चल रही है प्रिपरेशन। और यहाँ पर ESE में हम PYQ डिस्कस करने वाले हैं आज कम्युनिकेशन सिस्टम्स के। तो कम्युनिकेशन सिस्टम्स से आप लोगों को किस टॉपिक में सबसे ज़्यादा प्रॉब्लम होती है, विच आर द टॉपिक्स इन विच यू आर नॉट फीलिंग कंफर्टेबल फॉर ESE एग्जाम्स। एंड इन दिस सेशन विल बी स्टार्टिंग विद द टॉपिक रैंडम वेरिएबल्स। उसके पहले PYQs देखेंगे, फिर उसके बाद हम FM और AM में हम एंटर करेंगे। तो चलिए एक बार शुरू करते हैं अपने सेशन को। और इजी क्वेश्चंस आप जानते हैं ESE में जो क्वेश्चंस होते हैं वो आपके बहुत ज़्यादा मतलब कैलकुलेटिव क्वेश्चंस नहीं होते, आपको उनके पीछे का कॉन्सेप्ट पता होना चाहिए, देखते ही आपसे क्वेश्चन सॉल्व होते जाएंगे। तो चलिए स्टार्ट करते हैं सेशन को। जैसे जो फर्स्ट क्वेश्चन है हमारा एक असर्शन रीजनिंग वाला ये क्वेश्चन है, ये ESE 2002 का ये पेपर में था। असर्शन गिवन है आपको यहाँ पर, थर्मल नॉइज इन मैकेनिकल रेजिस्टर्स कैन बी कैरेक्टराइज्ड बाय गॉसियन प्रोबेबिलिटी डेंसिटी फंक्शन। ठीक है, तो ये फर्स्ट आपके पास गिवन है कि थर्मल नॉइज in metallic resistors can be characterized by Gaussian probability density function, and reason is given as power spectral density of thermal noise is essentially constant for a very large frequency range। ठीक है, तो जल्दी से एक बार मुझे कमेंट करेंगे इस क्वेश्चन के लिए आंसर आप लोगों को क्या लगता है, इसमें कौन सा ऑप्शन करेक्ट होना चाहिए। चलिए, तो आप लोग यहाँ पर साथ साथ अगर बताते चलेंगे, अपने ऑप्शंस देते रहेंगे, तो फिर आप ज़्यादा एडवांटेज ले सकते हैं इन सेशंस का। मीनवाइल यहाँ पर अगर हम देखें, यहाँ पर जो असर्शन गिवन है थर्मल नॉइज, तो एट फर्स्ट वी हैव टू नो व्हाट द थर्मल नॉइज एक्चुअली इज। सो ऑल द इलेक्ट्रॉन्स इन अ रजिस्टर आर इन मोशन, इन अ रैंडम मोशन। जितने भी हमारे इलेक्ट्रॉन्स होते हैं रजिस्टर्स में वो हमेशा क्या होते हैं, रैंडम मोशन में होते हैं। क्यों? क्योंकि उनकी अपनी कुछ थर्मल एनर्जी होती है। तो वो क्रिस्टल लैटिस से टकराकर जो नॉइज़, मतलब जो टेम्परेचर, जो टेम्परेचर वहाँ पर जो इंड्यूस करते हैं उसकी वजह से जो नॉइज़ आता है दैट इज़ नोन एज थर्मल नॉइज़। तो जितने भी इलेक्ट्रॉन्स हैं वो सभी रैंडम मोशन में हैं, उनका जो पाथ है वो रैंडम है, और उन सभी की वजह से एक नेट करंट जो फ्लो होता है वो एक रैंडम करंट होता है, मतलब जिसका डायरेक्शन रैंडम होता है और उसका जो मीन होता है वो एसेंशियली ज़ीरो होता है। तो ये जितने भी सोर्सेज हैं उन सभी सोर्सेज के नेट इफेक्ट की वजह से हमारा थर्मल नॉइज़ क्रिएट होता है। अब आपने सेंट्रल लिमिट थ्योरम पढ़ी होगी कि जब एक से ज़्यादा सोर्सेज होते हैं तो रैंडम सोर्सेज, तो उन सब की वजह से जो हमारी प्रोबेबिलिटी डेंसिटी फंक्शन बनती है वो इंडिविजुअल प्रोबेबिलिटी डेंसिटी फंक्शंस के कॉन्वोल्यूशन के बराबर होती है। और आपको ये भी पता है कि जब हम रिपीटेड कॉन्वोल्यूशन परफॉर्म करते हैं डिफरेंट जो प्रोबेबिलिटी डेंसिटी फंक्शंस हैं, तो अल्टीमेटली जो उसका शेप बनता है हमेशा ही वो एक गॉसियन होता है। तो रीज़न ये जो गिवन है आपका, इट इज़ एब्सोल्युटली करेक्ट। असर्शन जो गिवन है वो बिल्कुल करेक्ट है कि थर्मल नॉइज की जो पीएचडी है वो कैसी है, गॉसियन इन नेचर। ये बिल्कुल सही है कि गॉसियन नेचर में, लेकिन क्यों है नेचर में गॉसियन? ड्यू टू सेंट्रल लिमिट थ्योरम कि जितने भी सोर्सेज हैं उन सभी सोर्सेज के नेट इफेक्ट की वजह से थर्मल नॉइज हमें मिलता है। एंड ऑल द प्रोबेबिलिटी डेंसिटी फंक्शंस इफ यू आर गोइंग टू कन्वॉल्व रिपीटेडली विद ईच अदर, तो जो लास्ट में जो आपका फाइनल रिजल्ट होगा प्रोबेबिलिटी डेंसिटी फंक्शन का वो एक गॉसियन का शेप लेगा। तो अपने आप में असर्शन करेक्ट है और ये आपका रीजनिंग भी करेक्ट है कि पावर स्पेक्ट्रल डेंसिटी ऑफ थर्मल नॉइज इज एसेंशियली कांस्टेंट फॉर अ वेरी लार्ज फ्रीक्वेंसी रेंज। ये भी आपको पता है कि जो पावर स्पेक्ट्रल डेंसिटी है वाइट नॉइज की तरह, मतलब वो कांस्टेंट ओवर अ वाइड फ्रीक्वेंसी रेंज। तो असर्शन रीजन दोनों ही करेक्ट हैं, लेकिन ये रीजनिंग इस असर्शन का करेक्ट रीजन नहीं है। करेक्ट रीजन क्या है, क्यों होती है प्रोबेबिलिटी डेंसिटी फंक्शन ये गॉसियन हमारा क्यों होता है, ये मैंने आपको बताया ड्यू टू द सेंट्रल लिमिट थ्योरम। तो ये दोनों ही आपस अपने आप में करेक्ट हैं, लेकिन रीजनिंग करेक्ट नहीं है असर्शन का, तो आप ऑप्शन कौन सा सेलेक्ट करेंगे? ऑप्शन बी इज करेक्ट, बोथ ए एंड ए आर ट्रू बट आर इज नॉट द करेक्ट एक्सप्लेनेशन ऑफ ए। चलिए नेक्स्ट क्वेश्चन पे चलते हैं। तो द नेक्स्ट क्वेश्चन इज पावर स्पेक्ट्रल डेंसिटी ऑफ अ सिग्नल इज। देखिए हमेशा ही पीएचडी जब भी आप पढ़ते हैं तो आपको पीएचडी की प्रॉपर्टीज में आपने हमेशा ही पढ़ा है कि ये पावर स्पेक्ट्रल डेंसिटी, ठीक है, तो पावर स्पेक्ट्रल डेंसिटी इज ऑलवेज एन इवन फंक्शन ऑफ फ्रीक्वेंसी ओमेगा, ये पहली प्रॉपर्टी है। सेकेंड प्रॉपर्टी है इट कैन नेवर बी अ नेगेटिव क्वांटिटी, कभी भी नेगेटिव नहीं हो सकती। और तीसरी चीज़ ये रियल है, मतलब अगर आप देखें तो ये तीन प्रॉपर्टीज इसकी जो बेसिक प्रॉपर्टीज हैं उसी पर ये क्वेश्चन था आपका। सो पावर स्पेक्ट्रल डेंसिटी पीएचडी इज ऑलवेज रियल, इवन एंड नॉन नेगेटिव, मतलब ये जो बी ऑप्शन है यहाँ पर भी ये ऑप्शन बी इसके लिए करेक्ट है। तो पीएचडी से रिलेटेड आप अगर देखें तो मैंने इसी चैनल पर ईएसडी पीएचडी एनर्जी स्पेक्ट्रल डेंसिटी पावर स्पेक्ट्रल डेंसिटी पर डिटेल्ड वीडियो आपके लिए यहाँ पर शेयर किया बनाया हुआ है, आप अगर चाहें तो वो वीडियो भी देख सकते हैं। उसमें इनपुट पावर स्पेक्ट्रल डेंसिटी पता हो तो आउटपुट पावर स्पेक्ट्रल डेंसिटी क्या होगी, या इनपुट एनर्जी स्पेक्ट्रल डेंसिटी पता हो तो आउटपुट एनर्जी स्पेक्ट्रल डेंसिटी क्या होगी, ये सभी चीज़ें डिस्कस्ड हैं अच्छे से, तो आप उसको भी देख सकते हैं उस वीडियो को भी। अभी यहाँ पर सिर्फ बेसिक प्रॉपर्टी पर क्वेश्चन था, तो ऑप्शन बी इज करेक्ट फॉर क्वेश्चन नंबर 2। चलिए नेक्स्ट देखते हैं। नेक्स्ट क्वेश्चन गिवन आपको, अ माइक्रोफोन विथ इनबिल्ट एम्पलीफायर हैज एन आउटपुट नॉइज लेवल इन अ वेरी क्वाइट रूम ऑफ अबाउट 30 माइक्रोवोल्ट आरएमएस। द मैक्सिमम आउटपुट लेवल इज about 300 microvolt RMS before say where distortion occurs। तो यहाँ पर बोला गया कि अगर ऑलमोस्ट क्वाइट रूम है तब जो हमारे पास लेवल है वो कहाँ पर है 30 माइक्रोवोल्ट RMS, और जब बहुत ज़्यादा नॉइज़ है उस टाइम पर जो लेवल है वो कहाँ पर है 300 माइक्रोवोल्ट। तो पूछा गया कि व्हाट इज़ द डायनामिक रेंज डज दिस रिप्रेजेंट इन डीबी। तो जब हम वोल्टेज के लिए अगर डायनामिक रेंज देखना चाहते हैं तो इन डीबी आप लिख सकते हैं यहाँ पर वी कैन राइट डायनामिक रेंज in dB is equals to 20 log base 10, जो आपका मैक्सिमम जो दिख रही है वैल्यू वोल्टेज की आरएमएस और जो मिनिमम वैल्यू दिख रही है उन दोनों का रेशियो, तो यहाँ पर ये मिली वोल्ट्स में, तो अगर हम एक क्वांटिटी को मिली वोल्ट्स में लिख रहे हैं 300 मान लीजिए मिली वोल्ट्स, तो डिवाइडेड बाई इस क्वांटिटी को भी हम मिली वोल्ट्स में कन्वर्ट कर लेते हैं। तो अगर ये माइक्रो वोल्ट में गिवन है तो इंटू 10⁻³ करना पड़ेगा। सो 30 माइक्रो वोल्ट it can be written as 30 into 10⁻³ millivolts, so it is going to be 0.03 millivolts। तो अगर आपने यहाँ पर वैल्यू पुट कर दी 0.03, so it is going to be 20 log base 10⁻⁴। ये अगर आप देखें तो ये वैल्यू इसको आप इंटू 100 भी कर सकते हैं, तो ये वैल्यू कितनी आ गई 3 इंटू 10⁻⁴, 3 और 3 कैंसिल हो गए तो 10⁻⁴, तो ये वैल्यू आ जाएगी 4 और इट इज इक्वल्स टू 20 इंटू 4 दैट इज इक्वल्स टू 80 dB। तो ऑप्शन जो करेक्ट होना चाहिए दैट इज ऑप्शन डी। सो इवन इफ यू आर इंटरेस्टेड इन द डीवी वैल्यू ऑफ वोल्टेज और करंट देन विल टेक 20 लॉग, अगर यहीं पर पावर के टर्म्स में होता तो हम यहाँ पर 10 लॉग लेकर के कैलकुलेट करते। चलिए नेक्स्ट देखिए, a sinusoidal signal with a random phase is given by x of t is a sin pi/2 minus 2 pi ft plus theta with the probability density function rho theta of theta equals to 1/2 pi over the range 0 to 2 pi and it is 0 otherwise। तो पूछा गया what is the maximum amplitude of the autocorrelation function of this signal। ठीक है, जो लोग भी प्रेजेंट हैं बताते रहिएगा। सर कैन यू प्लीज़ कंप्लीट द होल कम्युनिकेशन डिजिटल प्लस एनालॉग इन one playlist, it will be very helpful for us, theory and concept, we can think about it, but for this we will be requiring some more students connected with us. If we will be having some good strength of students then we can definitely plan for this, otherwise there is no meaning for this these type of lectures. So if you see here we are having a sinusoidal signal with a random phase is given by x of t is a sin, as x of t is given as x of t is a sin pi/2 minus, let's say for simplicity if we take 2 pi f is equals to omega c, because I just want to show you the general result, that is if a function is a sinusoidal or cosinusoidal function then what is going to be its autocorrelation function. So if we write it like a sin pi/2 minus omega ct plus theta, where omega c we are considering as it is 2 pi f. 2 pi f For 2 pi f, I am writing omega c. So if you see here, sine pi by 2 minus theta is cos theta. So for simplicity, we can write it is equals to a cos of omega ct plus theta. So if a function x of t is a cos omega ct plus theta, where theta is the random variable which is having a probability density function that is equals to 1 upon 2 pi over the range 0 to 2 pi. So if we have to calculate autocorrelation function of this x of t, and then we have to find the maximum amplitude of autocorrelation function. So to reach to a general result, if a function is a cos omega ct plus theta, then what is going to be its autocorrelation function? We know that autocorrelation function Rx of tau, it may be written as expected value of x of t into x of t plus tau. So if we are having x of t as a cos omega ct plus theta, so we just have to calculate first x of t plus tau function, and then we'll be calculating the expected value of x of t into x of t plus tau, which is give you the autocorrelation function, and then we'll be seeing that what is the amplitude, maximum amplitude of this Rx of tau. So to find x of t plus tau, we are having x of t as a, is it a? Yes, a cos omega ct plus theta. So x of t plus tau will be what? If we replace t by t plus tau in the left hand side, then we'll be taking the same replacement on the other side as well. So it will be cos of omega c times t plus tau plus theta, which is going to give you a cos of omega ct plus omega c tau and plus theta. So it is x of t and x of t plus tau. Therefore, if we see the product x of t into x of t plus tau, so it is going to be a into a, that is a square, then cos of omega ct plus theta into cos of omega c t plus omega c tau plus theta. See, मैं आपको डायरेक्ट भी रिजल्ट बता सकता था कि यहाँ पर जो रिजल्ट आने वाला है वो डायरेक्ट भी हम देख सकते थे, लेकिन एक बार आपको पता होना चाहिए ऑटो कोरिलेशन फंक्शन हम कैसे निकालते हैं, इसलिए यहाँ पर हम इसको डिस्कस कर रहे हैं. तो अगर आप इसको देखेंगे तो यहाँ पर अब आप यूज़ कर सकते हैं cos a इंटू कॉस बी का रिजल्ट. 2 cos a इंटू कॉस बी इज इक्वल्स टू cos of a माइनस बी प्लस cos of a plus b. So cos a into cos b, it may be written as a square into, if there would be 2 cos a cos b, then we can use the formula cos of a minus b plus cos of a plus b. If we are having only cos a cos b, so let's say we are converting into a square into 2 divided by 2. We can do like this. Therefore, if it is a square only, a square cos, so we can write it like a square by 2 times cos of a minus b, that is omega ct plus theta, minus of this value minus omega ct minus omega c tau minus theta, and plus cos of a minus b, first we have written, then we have to write plus cos of a plus b, which is equals to omega ct plus theta plus omega ct plus omega c tau and plus theta. So now finally we are going to get a square by 2 into cos of, here theta and theta will get cancelled, omega ct and omega ct will get cancelled. So you are having cos of minus of omega c tau. And as we know, cos of minus theta is equals to cos of theta, so you can write cos of omega c tau as well. And the next term is plus cos of, here if you see, omega ct plus omega ct is 2 times omega ct plus omega c tau and plus 2 theta. So if you are adding these two values, then you are going to get 2 omega ct plus omega c tau plus 2 theta. So we have to find expected value of this, that is xt into x of t plus tau. And to find expected value, if you finally write it like, you can write it a square by 2 times cos omega c tau, as cos of minus theta is cos theta only, and plus it is cos of, let's say, as we are going to find expected value in terms of theta for the values of theta. So if this term is independent of theta, then it may be taken as a constant, because we are going to integrate it with respect to theta. So this term will be treated as a constant with respect to theta. So let's say this value is anything you can assume. Let's say it is x plus, or x we are already having. So let's say it is z plus theta. So this complete term is independent of theta. So if you are going to find expected value of any constant function, then it is going to be itself only. So for this part, as you can write it finally, that is x of t into x of t plus tau. Now you are having it as a square by 2 times cos of omega c into tau, and plus a square by 2 times cos of z plus theta, where z is what? Z is 2 cos, it is z is 2 omega ct plus omega c tau. 2 omega ct plus omega c tau. So to find expected value, expectation of x of t into x of t plus tau, it is equals to integration from minus infinity to plus infinity. As we are going to get expected value in terms of theta, so it is whatever the value of x of t into x of t plus tau, x of t plus tau into rho theta of theta d theta. So for the first term, if you see here, this complete term is independent of theta. So this complete term will be treated outside the interval, and we are having rho theta of theta as rho theta of theta is given to be 1 upon 2 pi. That is uniformly, it is distributed uniformly over 0 to 2 pi range, and it is equals to 0 otherwise. So this integration from minus infinity to plus infinity, you can change it over only from 0 to 2 pi, because this function is non-zero only this interval 0 to 2 pi. So it is going to be integration, and this value rho theta of theta is 1 upon 2 pi, which is constant, so it can taken outside from the integral. So it is 1 upon 2 pi from 0 to 2 pi, and the value of xt plus x of t plus tau, you are having a square by 2 cos omega c tau, and plus a square by 2 cos of z plus theta into d theta. So if you see, for the first term, what we can see is, here the value is going to be 1 upon 2 pi into, for this term, this complete term a square by 2 cos omega c tau can be taken outside from the integral. So integration will be from 0 to 2 pi of d theta only. And for the next term, you can see here, it is a square by 2 into cos of integration from 0 to 2 pi, this cos of z plus theta d theta, right? So if you see here, it is a cosine function which is integrated over integral multiple times of its time period. So the area under the cosine function or sinusoidal function for one time period or any integral multiples of time period is always going to be 0. So this part of integral will result into 0. This part will result into 0. The value of this part is 0, as area of cosine for integer number of time period, it is going to be 0. So now we are left only with the first part, and for the first part you can see is expected value of any constant function is itself only. So it is going to be what? Here if we integrate d theta, then you are going to get theta, and in theta if you take limits from 0 to 2 pi, so it will give you 2 pi, and this 2 pi and 2 pi will get cancelled. So finally you are going to get expected value, that is nothing but your expected value of x of t and x of t plus tau, that is nothing but autocorrelation function Rx of tau. So now you are going to get it as a square by 2 times cos of omega c tau. This part is 0, and for this part if you evaluate the integral, then this integral will result into 2 pi, and this 2 pi and 2 pi will get cancelled. Therefore finally you will be having a square by 2 times cos of omega c tau. So it is the value of autocorrelation function. And if you see here, autocorrelation function is again a cosine function, and its amplitude, that is maximum value of amplitude, you have to find out. And you also already know that maximum value of autocorrelation function occurs if you put tau is equals to 0. Or even if you see here, that maximum value of cosine function will be occurring at if the theta, that is omega c tau, if you will be taking this value as 0. So a square by 2 times cos of 0, that is equals to 1, will be the maximum value of autocorrelation function. So you can write from here that if Rx of tau is a square by 2 into cos of omega c tau, if you put the value of omega c that we have taken, that is a square by 2 into cos of 2 pi f tau. We have taken omega c to be 2 pi f. So finally it is your answer for autocorrelation function, and therefore maximum value of Rx of tau, then it is equals to a square by 2 into cos of 2 pi f tau, maximum value of this function. And you know that the maximum value of cosine function is nothing but 1, or you can also write it like maximum value of Rx of tau is going to be Rx of 0 only. That is if you put the value of tau equals to 0. So it is going to be a square by 2 into 1, that is equals to a square by 2. So finally we have got the result, that is if the signal x of t is a sine pi by 2 minus 2 pi t plus theta, and it is having probability density function given to be a uniformly distributed between 0 and 2 pi, then the maximum amplitude of autocorrelation function will be a square by 2, and accordingly option D is correct. I hope all of you can get it. Yes, D option is correct. रवि बिल्कुल सही आपका आंसर. चलिए तो नेक्स्ट क्वेश्चन पर चलते हैं. और नेक्स्ट क्वेश्चन अगर आप देखें, पूछा गया white noise is passed through an ideal low pass filter. Which one of the following is the nature of the autocorrelation function of the filtered output noise? So if you say, we have to find the autocorrelation function of output noise. If you are passing a noise, let's say with PSD, if white noise is passed, so white noise is having a PSD that is constant over the wide frequency range, that is eta by 2. Let's say if you see PSD of white noise is something like this. It is eta by 2, that is if you take magnitude of h of, so it is PSD of white noise. Let's say it is SIX. With respect to frequency we are talking. So with respect to frequency, it is input PSD. In a low pass filter, we are applying white noise as an input, which is having a PSD that is constant over a wide frequency range. So if you pass a PSD through an LTI system, and LTI system is nothing but an ideal low pass filter. So ideal low pass filter is having a characteristics, that is, if you see ideal low pass filter, let's say you are plotting h of f for an ideal low pass filter. So it will be passing up to some frequency as fc, from 0 to frequency fc it will be passing with gain 1, and it will be blocking all the frequencies more than fc. So it is the magnitude of transfer function for an ideal low pass filter. So it is having from minus fc to fc. So if you pass a noise PSD, which is white noise having PSD eta by 2, through a filter which is having characteristic like this, then output PSD is given as, you know that output PSD, that is SY of x is equals to input PSD into magnitude of transfer function whole square, HF whole square into SF of SX, SI of x. It is the output PSD value. So if you are going to multiply these two, it is your SI of f. Let's say it is your SI of f. We can take f in terms of f. For input, let's say it is SX of f, and for output, let's say it is SY of f. So it is SI of f having value eta by 2, and if you are going to square this HF, then as the value is 1, so square of 1 will be 1 only. So it is H of f whole square from minus FC to plus FC. So the product of these two will be resulting in this. That is eta by 2 into 1 will result into eta by 2 only. So it is SY of f from minus FC to plus FC from f. So we are having output PSD. Why we have obtained the output PSD? Because Wiener-Kitching theorem, if you see, then Wiener-Kitching theorem says that autocorrelation function and power spectral density forms an Fourier transform pair, a Fourier transform pair. So if you find out the output PSD, then output PSD is SY of f. It is nothing but it is Fourier transform of power spectral density, that is output autocorrelation function. So if you have to find out the autocorrelation function, then Ry of tau, let's say, then it is going to be inverse Fourier transform of this output PSD, that is inverse Fourier transform of SY of f. Now you know that if in one domain a particular quantity is rectangular, then definitely in the other domain it will be sinc or sampling function. And we have already discussed in the class of signals and systems that, please wait, that is, if we are having that is, let's say from minus tau to tau, if it is t minus tau by 2 to tau by 2, it is a, the value is a. So if it is a rectangle of t upon tau, this signal is a rectangle of t upon tau. So a rectangle of t upon tau will have a Fourier transform, that is a tau sampling of omega tau by 2. Or if you write in terms of f, then it is a tau sampling of, for the value of omega you can take 2 pi f. So 2 pi f upon 2 will be giving you pi f tau. It means if you are having a Fourier transform which is a tau sampling of pi f tau, then its inverse Fourier transform will be a rectangle of t upon tau. Now here if you see, you are having output PSD, and PSD from and if you have to find autocorrelation function, then autocorrelation function will be inverse Fourier transform of this. So if you see here, if you apply duality, you can apply duality as well. That is, if a rectangle of t upon tau is having a Fourier transform this, so if you will be having, if you apply duality, applying duality, that is a tau sampling of omega t into tau divided by 2. If we replace this omega by t in the frequency domain, then this time domain signal will have a Fourier transform that will be equals to 2 pi times a into rectangle of, at the place of t we have to take minus omega, but as the rectangular function is an even function, so even if you put either omega or minus omega, the result will be same. So you can take omega by tau. So if we are having 2 pi a rectangle of, you can write it like 2 pi f divided by tau, that is 2 pi f upon tau. Then you'll be having its inverse Fourier transform as a tau sampling of t into tau by 2. So see here, a rectangle of f upon tau. So you are having this function. If you write it in the form of rectangular function, then what you can write it like sy of f. It may be written as, at the place of a, you are having the value eta by 2. So it is eta by 2 a rectangle of f upon tau, and the tau value is minus fc to fc. This total width is tau, so it is going to be twice of fc. So at the place of tau, you are having 2fc. So you have to take inverse Fourier transform of eta by 2 times rectangle of f upon 2fc. We have to take Fourier transform inverse of eta by 2 times rectangle of what? F upon 2fc. F upon 2fc. See here. If you see, we just have to find out the values of a and tau. Then we can write it a tau sampling of t tau by 2. So what is the value of a? A into tau is equals to, here it is, 2 pi a times. So 2 pi a is equals to eta by 2. And it is f upon 2 pi f upon tau. So if you see here, 2 pi f upon tau. 2 pi upon tau is equals to 2 pi upon tau. F and f are common in both the values. So 2 pi upon tau is equals to 1 upon 2 pi fc, 2fc. 1 upon 2fc. Therefore, if you see the value of tau, then tau is equals to what? So tau is equals to 2 pi into 2fc. That is equals to 4 pi fc. So you have obtained the value of tau as 4 pi fc. To find the inverse, we need to have the values of a and tau. Then we can write the inverse of this function as a tau sampling of t tau by 2. So we have find out the value of tau, and tau is equals to 4 pi fc. Now, if you write the value of a, so if you compare these two values, 2 pi a is equals to 2 pi times a is equals to eta by 2. Therefore, a is equals to what? A is equals to eta upon 4 pi. A is what? Eta upon 4 pi. Therefore, if you want to write now the inverse of this function, then it is going to be a tau. At the place of a, you can write eta upon 4 pi into, at the place of tau, you can write 4 pi fc into sampling of t into tau. Tau is 4 pi fc divided by 2. So finally, it is going to be the inverse of this PSD. That is, if it is PSD, then it will be representing the autocorrelation function. So finally, what we are going to get is this 4 pi and 4 pi will get cancelled, and we are going to get output correlated autocorrelation function Ry of tau. It is equals to eta times fc into sampling of, you can see here, it is 2 pi t into fc. That is 2 pi fc into t. So this is our autocorrelation function. And now we are having some statement about this autocorrelation function. If you see this autocorrelation function which we have obtained is, it is equals to eta times fc into sampling of 2 pi fct. 2 pi fct. Now see, sampling function is having a shape like this. It is the shape of sampling function. And this sampling function will be crossing 0 values. If you see, in terms of t, not t, it is tau. So this sampling function can sampling of x, you know that sampling of x, it is going to be sin x upon x. It is equals to sin x upon x. So at the place of x, we are having 2 pi fct. So it will be eta fc into sine of 2 pi fct upon 2 pi fct. This tau actually, because we are taking inverse in terms of tau, so it will be tau, not t, it will be tau. So the value is in terms of tau. So if you see here, it is divided by 2 pi fc tau. So this sine function will be 0 whenever the value of theta is either pi or any integer multiples of pi. So this function ACF will be 0 if this numerator term sine 2 pi fc tau is equals to 0. Whenever sine 2 pi fc tau will be 0, then this numerator will become 0. Therefore, the total autocorrelation function will also become 0. So when this function will be 0, if 2 pi fc tau, if this 2 pi fc tau is plus minus n pi, it is equals to plus minus n pi, except for n equals to 0. You cannot take the value of n equals to 0, because at 0 the autocorrelation function is having the maximum value, which is equals to nothing but eta into fc. The maximum value will be eta times fc when you put the value of n equals to 0 in this equation. So you can take only non-zero value of n. So if you see here, this pi and pi will get cancelled, and this tau is equals to plus minus n upon 2 fc. Plus minus n upon 2 fc. At these in values of tau, you will be having autocorrelation function equals to 0. If you put n equals to 1, so you're going to get plus minus 1 upon 2 fc. If you put fc n equals to 2, so you will be having 2 upon 2 fc, that is plus minus 1 upon fc. If you put n equals to 3, then you will be having 3 upon 2 fc plus minus 3 upon 2 fc, and you keep on increasing the value of n, and you will be having the zero crossing points, that is for the values of tau, for which values of tau this autocorrelation function will become 0. So the next values will be 4 upon 2, that is 2 upon fc, and so on. So you see here it is 1 upon 2 fc, this point is minus 1 upon 2 fc, it is plus 1 upon fc, this point is minus 1 upon fc, and so on. It is 3 by 2 fc, this point will be minus 3 by 2 fc, and so on. So if you see, autocorrelation function is having zero crossing points as at equal intervals of frequencies. So for this given question, if you have to select options, then what we have seen here is, if white noise is the input PSD, then output PSD will be same like the value of transfer function. As you have seen here, it is the output PSD which is rectangular in shape. Therefore, autocorrelation function will be sampling in shape, and you have obtained the expression for the sampling function. It is the output autocorrelation function, which is a sampling function in itself, and this sampling function is going to cross zeros after every finite interval of frequencies of tau. Therefore, you can see that the final result from this option, that is, which one of the following is the nature of the autocorrelation function of the filtered output noise? Nature of output noise autocorrelation function is, it is having periodic infinite number of zero crossings, and it is absolutely correct, because the zero crossings are at periodic intervals of tau. Autocorrelation is not periodic, but zero crossing is periodic in nature, and it has infinite number of zero crossings. If you see the other option, periodic, but the number of zero crossing depends on the bandwidth of the filter. No, always there will be infinite number of zero crossing if the function is sync or sampling function. So option B is not correct. Option C is periodic but does not cross zero. It is absolutely wrong, because the autocorrelation function will be crossing 0 point infinity number of times. A delta function is also not correct, so option A is correct for this given question. प्रभुदत्त, आपसे मैंने उस दिन आपके लास्ट में पूछा था कि आप प्रेजेंट हैं या नहीं, उस दिन आप नहीं थे। आप मुझे फिर कॉल कर लीजिए, मैंने आपको कॉल पे बताया भी आपके क्वेश्चन का सॉल्यूशन। वो कोई इतना बड़ा क्वेश्चन नहीं है, चलिए मैं आपको बता ही दूंगा, ठीक है? थोड़ा सा वेट कर लीजिए, मैं बता दूंगा आपको। चलिए नेक्स्ट क्वेश्चन देखिए, क्वेश्चन नंबर 6 हमारे पास। व्हेन जीरो मीन गॉसियन नॉइज ऑफ वेरिएंस n इज अप्लाइड टू एन आइडियल हाफ वेव रेक्टिफायर, व्हाट इज द मीन स्क्वायर वैल्यू ऑफ द रेक्टिफाइड नॉइज? व्हेन अ जीरो मीन गॉसियन नॉइज, what we are having is, we are having an ideal low pass filter, ideal low pass filter, and input to this low pass filter is a Gaussian noise or normal distribution, you can say Gaussian noise, which has characteristics zero mean, mean is 0 and variance is n. Variance is n. We are going to pass this noise, zero mean wide Gaussian noise, to an ideal low pass filter, ideal half wave rectifier. It is given half wave rectifier, and you know the property of half wave rectifier, that is, if input is x, let's say for input x, output of half wave rectifier is what? Output y is equals to x only if x is greater than or equals to 0, and it is 0 if x is less than 0. You know that half wave rectifier is going to pass only the positive half cycle if it is a sinusoidal waveform, or if it is having any other shape, then you can say that if input is x, then whenever input is either positive or 0, then output will be x only, that is input only, but output will be 0 if the input is less than 0, that is negative. So we have to find the value of, what is the mean square value of the rectified output? Mean square value, that is expected value of x square. For output, we have to find expected value of y square. Expected value of y square. So if a random variable is having zero mean and variance n, then you know that variance sigma x square, it is equals to, it is also known as AC power. It is AC power, and it is equals to total power minus DC power. Total power minus DC power, that is equals to, total power is expected value of x square if the random variable we are taking as x, and then minus DC power is expected value of x whole square, that is mean square of the mean. It is your DC power, and if you are having expected value of x, that is mean equals to 0. So if mean is 0, it is nothing but your mean. So if mean is 0, then this DC power is equals to 0, and in that case AC power is nothing but, that is your variance. Variance gives you the total power, that is mean square value. So if mean is 0, then total power or total power is equals to mean square value, that is equals to expected value of x square only. So in this case we are having a zero mean Gaussian noise. So the power of this Gaussian noise is nothing but equals to its variance only, that is input power is equals to n only. So input power we are having, therefore input power, if you see, then this input power, that is, if we are expecting representing input by x, then it is equals to expected value of x square, then it is equals to variance only sigma x square, and that is equals to nothing but n, which is given to be n. Variance is given to be n. So if the variance is n, input power is n, if you are passing, let's say that the input is a cosine function. If you consider that input is a cosine function, I'm going to discuss it by another method as well, but for the sake of simplicity, if you take, let's say, let us consider input as a cosine function. Let's say it is a cos omega ct. If you are having any cosine function is input in input, then it is going to has a power. It has a power that is equals to what? A square by 2, or if you take AC, so it is AC square by 2. So this power is going to be is equals to n. Let's say it is n. It is given from the given statements in the question. If input is having total power equals to its AC power only, as the DC power mean is 0, so DC power will be 0. So the total power in input is equals to n. So if we consider the input as an cosine function, AC cos omega ct, so it will be having power value that is AC square by 2. So it is going to be equals to n, that is your value of variance, that is equals to AC power. So if AC square by 2 is n, therefore the amplitude of input signal AC is what? Therefore AC is equals to, if you see AC square, then it is equals to 2n, therefore AC equals to under root of 2n. So you have obtained the amplitude of input signal equals to what? 2n. So input that you are going to pass through a ideal half wave rectifier, if you are going to pass an input which is AC cos omega ct, that is equals to under root of 2n into cos omega ct through a half wave rectifier. So the output of this half wave rectifier, if you see the RMS value of output of rectifier, then RMS value of output voltage will be what? RMS value of output. It is equals to what? Amplitude of input divided by 2. You know that if input is having an amplitude that is equals to AC, then the output RMS value will be what? AC by 2. So it is going to be AC by 2. That is nothing but under root of 2n divided by 2. So if you have obtained the RMS value of your output, that is under root of 2n by 2, therefore output power will be what? Therefore output power, that is output power is equals to RMS output RMS value of output whole square. Power is always equals to RMS value whole square. So if you are having RMS output value as under root 2n by 2, so it is going to be what? Under root of 2n by 2 whole square. So it is going to be 2n divided by 4, that is equals to n by 2. And as input is having 0 mean, so output will also have 0 mean. Therefore the output power is nothing but the mean square value of the output. Therefore this output power, therefore you can write mean square value of output. Mean square value of output, that is equals to AC power only. AC power of output, you can also write it AC power of output as mean is 0. As mean is 0. If mean is 0, then DC power is 0. Therefore total power in output is its AC power only, that is equals to its mean square value in this case, and it is going to be what? N by 2. So the correct option is N by 2. If you see the options, then in options we are having what is the mean square value of rectified noise. So output noise will have power that is equals to N by 2. So option B is correct for this question. Are you understanding what I am trying to explain? Or you can also see here, that is if you are writing that is input is what? It is a Gaussian variable with mean 0 and variance n, right? So if you have to find output, mean square value of output, mean square value of output. So output is what you have already written, that is output y is going to be x only if x is greater than 0, and it is 0 if x is less than 0. So you can write that y is equals to maximum of 0 and x. Either y is going to be 0 or it is going to be x. If x is greater than 0, then only the output y is going to be x. That is, you can write output y is maximum of 0 and x. So if you have to find mean square value of output, then it is going to be what? That is expected value of y square. Then it is going to be integration from minus infinity to plus infinity, y square into rho y of y into dy. So if you see here, you are having a Gaussian PDF. So Gaussian PDF is what? If you see here, rho y of y, that is equals to 1 upon under root 2 pi sigma x square into e to the power x minus of x minus mx, that is mean, whole square upon 2 sigma x square. So if mean is 0, then it is going to be what? 1 upon under root 2 pi n into e to the power minus of, in case of y, you can write it rho y of y. So it is minus of x upon 2x. So if you put the value for the range, that is y is maximum of 0 and x, you have to take square of this value from minus infinity to plus infinity. And for this value, you can write 1 upon under root of 2 pi n into e to the power minus x upon 2n dx. So for 0 to infinity, if you take the range from 0 to infinity, so this value will be what? It will be, in the duration from 0 to infinity, x will be greater than 0. So you can write it like integration. If you are taking from 0 to infinity, then you can write x square into 1 upon under root 2 pi n into e to the power minus of x upon 2n into dx. And this integral will be resulting into n by 2. It is the standard integral. If you evaluate this standard integral, then it will be resulting in the value n by 2. So from this method also, you are going to get the same value, that is mean square value of output will be what? It will be n by 2 only. So no need to follow this method. You just have to understand the first method as well only, that if input is having 0 mean PSD with variance sigma x square equals to n, so input power, that is total power, is equals to its AC power only, that is equals to sigma x square, that is equals to n. So n is the input power. So if we consider input as AC cos omega ct, so its power, that will be a square by 2 is given to be n. Therefore the amplitude of input AC can be considered to be under root of 2n. So if it is the amplitude of input, so output of half wave rectifier will be having an RMS value that is equals to AM upon 2. Therefore the output RMS value will be AC by 2, that is equals to under root of 2n by 2. If you are having the RMS value of output, then you can simply calculate the power of output by taking RMS square. Therefore the output power, or you can say mean square value of output, is going to be under root 2n divided by 2, which is the output RMS value, whole square, and it is going to give you n by 2. So the option B is correct for this given question. So n by 2 is correct option. Moving to the next question, it is given to be if two registers of values R1 and R2. If we are having two registers, please wait. Two registers of values R1 and R2 at room temperatures T1 and T2 are connected in series to form a white noise source. The equivalent noise temperature is. Again, here we are having a problem on thermal noise. So if you see, if two resistors are in series, then total noise power generated by two resistors in series is equals to what? This total noise power is equals to what? You know that noise power is KTB. So it is going to be, for resistor R1, the noise power will be K, where K is Boltzmann constant. into temperature at R1 is having a temperature T1 and R2 is having a temperature T2. So it will be KT1 R1 into B plus KT2 R2 into B. So it is the total noise power. This is going to be the total noise power. So now if you have to find out the equivalent noise temperature, let's say the equivalent noise temperature is T equivalent. So total noise power can also be written in terms of total noise power. Now if you write it in terms of equivalent noise temperature, that is T equivalent. So it can be written as K into, at the place of T you will be writing T equivalent, into at the place of R. Now these two resistors are in series, so for their equivalent resistance we are writing, let's say, R equivalent, where this R equivalent is equals to T1 plus R1 plus R2 only. In series the total equivalent resistance is sum of all the resistances. So K into T equivalent into R equivalent into B, that is bandwidth. So it is the total noise power if we calculate in terms of equivalent noise temperature, and it is the total noise power if we calculate it individually generated by resistor R1 and generated by resistor R2. So these two value must be same. Therefore if we equate these two equations, then we will be having, that is K into T equivalent into R equivalent into B, it is equals to K into T1 into R1 into B plus K into T2 into R2 into B. If you simplify it, that is, if you take K into B common, then it will be T1 R1 plus T2 R2, and from this side if you take K into B, then you can write T equivalent into this R equivalent can be written as R1 plus R2 in case of series resistors. So this K into B will get cancelled from both the sides, and therefore you are going to get T equivalent is equals to T1 R1 plus T2 R2 divided by R1 plus R2. And accordingly, if you see, then T1 R1 plus T2 R2 divided by R1 plus R2, which is given in option A. So this option A is correct for the given question. Next, consider the following statements if thermal noise power generated by a resistor is proportional to. See, thermal noise power when we are talking about, then this Pn, it is proportional to P is equals to KTB, where this K is proportionality constant. This actually Pn is proportional to B, Pn is proportional to T. So B is bandwidth, T is equivalent temperature. So at the place of, if we take the proportionality constant, then this Pn is equals to KTB. So you can also say that the Pn is proportional to this Boltzmann constant as well. This K is Boltzmann constant, and it is equals to 1.38 into 10 to the power minus 23 joule per coulomb, joule per Kelvin. So if you see here, then this noise temperature, if you are going to take this statement about noise voltage generated, then it is going to be KTB times R. Then the noise voltage is also proportional to the resistance. But noise voltage generated, if you see, then Vn is equals to under root of 4 KTBR. But it is noise voltage. It is what? Noise voltage. So even if we are considering only thermal noise power, not noise voltage, then this noise power is proportional to Boltzmann constant, equivalent temperature, and the bandwidth. So if you select the options, the value of the resistor is not correct, because we are not talking about the noise voltage, we are talking about the noise power generated. So resistor value, it will not be affecting the noise power. The absolute temperature is correct. The bandwidth over which it is measured is correct, and the Boltzmann's constant is correct. So these three are the correct statements. Therefore 2, 3 and 4 will be the correct option for this given question, and accordingly option D is correct. Moving to the next question, it is given as a communication channel is to receive signal power S, and the noise at the receiver input is additive thermal noise with uniform power spectral density. With uniform power spectral density, it is found that if the bandwidth is 1 megahertz, the channel capacity is 10 megabits per second. Mbps 10 Mbps given है आपको. What would be the channel capacity for the same signal power and same noise PSD if the bandwidth is unlimited? So basically it is a problem on bandwidth SNR trade-off ratio. If you have learned this concept, that is, if you are talking about the channel capacity, then channel capacity is given by C is equals to B log base 2 1 plus S by N. That is, channel capacity is equals to bandwidth times log 2 1 plus signal to noise ratio. So from this equation, if you see, it seems like if we are going to take infinite bandwidth, then this channel capacity will be infinity. But it is not the case, because if you are going to increase the bandwidth, then the noise passing through that frequency bandwidth also be increasing, and therefore total signal to noise ratio will be decreasing. Therefore this channel capacity will not be infinity. So even if you take the value of bandwidth to be infinite, this channel capacity tends to a finite constant value, and that is equals to, if for it is known as bandwidth SNR trade-off. Bandwidth SNR trade-off. That is, for B tending to infinity, channel capacity is not equals to infinity. Channel capacity is, in this case, channel capacity is given by 1.44 times S upon eta. Here if you see, it is signal power upon noise power. This N is equals to KTB. It is thermal noise power, that is equals to KTB, that we have already discussed in the previous slide. So at the place of KT you can write eta. So it is equals to eta into B. So N equals to eta into B, therefore channel capacity is equals to B log base 2 1 plus S upon eta B. So if you find out the value of S upon eta, then by taking 1.44 times S upon eta, it will give you the channel capacity in case of infinite bandwidth. So from the given first condition, you have to find out the value of S upon eta from this case, and then you will be using the value of S upon eta in this equation to find the value of channel capacity in the case of unlimited bandwidth. So from the given condition, we are taking it on the other page, that is C is equals to B log base 2 1 plus S by eta into B. Given channel capacity C is what? It is given to be channel capacity. It is found that if the bandwidth is 1 megahertz, the channel capacity is 10 Mbps. Channel capacity is 10 Mbps, that is 10 into 10 to the power 6. Bandwidth is given to be 1 megahertz, that is 10 to the power 6 hertz. Bandwidth is 1 megahertz if the channel capacity is 10 megapps. So if you put the values in this equation, so this 10 into 10 to the power 6, it is equals to B, that is 10 to the power 6 into log base 2 1 plus S upon eta into B. I am not writing the value of B here. If you want to write, then you can also write here. So if you see, this 10 to the power 6 will get cancelled from both the sides. As it is log base 2 1 plus S by N is equals to 10. Therefore, if you write only 1 plus S by eta B, then it is equals to, it is the base, so the value will be 2 to the power, here the value is 10, so it is going to be 2 to the power 10. This 1 is negligible if we compare it with S upon eta B, so you can neglect this one value and you can say that S upon eta B, it is going to be almost equals to 2 into 10 to the power 10. Therefore, you can find the value of S upon eta, that is required to find the value in case of if you are trying to find the value of channel capacity in case of infinite bandwidth. So S upon eta value is equals to 2 to the power 10 into value of bandwidth, and the bandwidth is 1 megahertz, that is 10 to the power 6 hertz. So if you take 2 to the power 10, it is going to be 1024. So it is going to be 1024 into 10 to the power 6. Therefore, now using bandwidth SNR trade-off, channel capacity for bandwidth tending to infinity, C is equals to what? 1.44 times S upon eta. So it is going to be 1.44 times S upon eta value is 1024 into 10 to the power 6. And if you calculate it, so if you are going to calculate this value, 1024 into 1.44 is going to be 1474.56 into 10 to the power 6. So if you see the options, then we are having option in Mbps, that is 15, which is not correct. 0 and infinite are not correct. So their option must be 1.5 Gbps. So if you Gbps means if you have to find out the values in terms of 10 to the power 9, so you can write it 1.474 into 10 to the power 3 into 6, that is 10 to the power 9. So it can be written as, that is nearly, it is nearly equals to 1.5 Gbps. And accordingly option D is correct for this given question. 1.5 Gbps is correct. Moving to the next question. I hope everything is going right. Okay. So the next question is, if ACF denotes the autocorrelation function and PSD denotes the power spectral density, then for white noise ACF is. For white noise, we know that PSD is what? Constant. PSD is eta by 2, that is constant. So, and you also know that Fourier transform of autocorrelation function will give you the PSD. So if PSD is constant, then you know that if any quantity is constant in one domain, then definitely it will be an impulse in another domain. It means if PSD is constant, then definitely Rx of tau, that is autocorrelation function, must be having impulse value. Then only the PSD can be constant. Therefore, Rx of tau will be a delta function. You know that. That is, if del t, for del t, the Fourier transform is what? 1, which is equals to constant. So constant in one domain represents impulse in other domain. It is the area of impulse function 1, then it is having the value 1. So if PSD is constant, it indicates that autocorrelation function must have an impulsive function. Therefore, a delta function, ACF is a delta function, while PSD is uniform, is the correct option. So option B is correct for this question. Next, a system has a receiver noise resistance of 50 ohms, it is ohms. It is connected to an antenna with an output resistance of 50. The noise figure of the system is. So it is the direct formula for noise figure, that is 1 plus R equivalent upon RS, that is equals to 1 plus, both of these values are equivalent noise resistance is 50 and antenna resistance is again equals to 50 only. So it is 1 plus 2, that is going to 1 plus 1, that is going to give you, and accordingly option B is correct. Next, a pre-emphasis circuit provides extra noise immunity by boosting the base frequencies. Actually, this pre-emphasis circuit it is used in FM. In FM, the noise is basically present as mainly, or you can say that noise is dominant at higher frequencies. So the higher in FM broadcasting, at first we boost higher frequencies before modulation, before the transmission, and then at the receiver end we use de-emphasis circuit. We will attenuate the higher frequency components. So used in FM, noise is dominant at higher frequencies. Therefore, high frequency components pre-emphasis, what this pre-emphasis circuit does is boost high frequency components before transmission. At receiver, we are having de-emphasis. That is, attenuate high frequency components. So if you see the options, that is, boosting the base frequencies is not correct. Amplifying the higher audio frequencies is the correct option. Pre-emphasis, what we does is we boost higher frequency components because the noise is severely present at higher frequencies. Therefore, amplifying higher audio frequencies is correct. Pre-amplifying the whole audio band is not correct. Converting the phase modulation to FM is not the correct option. So the option B is correct for this given question. Next, if you see, how many bits are required in an A to D converter with B+1 quantizer to get a signal to quantization noise ratio of at least 90 dB for a Gaussian signal with range of ±3 sigma x. Gaussian signal, we consider a Gaussian signal having zero mean. So if you see, signal to noise ratio is what? Signal power, that is power of signal upon power of noise. Signal to noise power ratio we have to calculate. So signal power PS, that is signal power. PS, that is equals to signal power. In case of zero mean Gaussian signal, the signal power is equals to what? Mean square value, that is equals to variance only. So it is equals to sigma x square. That is, if DC power is 0, mean is 0, therefore total power is equals to variance, that is equals to AC power only. So the signal power is going to be what? Sigma x square. Now you know that quantization noise power, PN, that is quantization noise power, is equals to S square by 12, where S is equals to what? Step size, and this step size is equals to what? Total peak to peak value divided by total number of levels, that is peak to peak value divided by number of levels. So let's say if you are having a total peak to peak value, that is 20 volts, and if you are dividing this 20 volt into 5 parts, then each level will have a step size of what? 20 divided by 5, that is equals to 4. That is what we are doing here. That is, if peak to peak value is, here we are having with range ±3 sigma x, that is peak to peak is -3 sigma x to +3 sigma x, that is equals to what? 6 sigma x. So 6 sigma x is the peak to peak value upon number of levels is equals to what? 2 to the power n. This n we have to find out. We just have to evaluate the value of n only. So if S is equals to 6 sigma x upon 2 to the power 2n, then quantization noise power is going to be what? It is equals to 6 sigma x divided by 2 to the power n whole square divided by 12. So it is going to be 36 sigma x square divided by 2 to the power, you can write 2n, square of 2 to the power n. Either you can write it like 4 to the power n, or you can also write 2 to the power 2n into 12. So if you cancel it, then noise power we are getting as, from 12, if you cancel this 36, so it will be 3 times sigma x square divided by 2 to the power 2n. So we have obtained quantization noise power, we have obtained signal power. So now we can find signal to noise ratio, that is signal power to noise power ratio. So the SNR is going to be, therefore SNR, signal power is sigma x square divided by noise power is 3 sigma x square divided by 2 to the power 2n. Noise power we have obtained is 3 sigma x square upon 2 to the power 2n. So this 2 to the power 2n will come into numerator. Sigma x square and sigma x square will get cancelled. So it is going to be what? 2 to the power 2n divided by 3. So if it is absolute value of signal to noise power ratio, therefore if you have to take SNR in dB, then it is equals to 10 log, that is equals to 10 log 2 to the power 2n divided by 3, that is equals to 10 log base 10 only, it is 2 to the power 2n minus 10 log base 10 3. So if you calculate the values, you can write it also like this 2n, this power may be taken as the coefficient, so it will be 20n into log 10 base 2 minus 10 log base 10 3. So it is going to be 20n into log 2. So if you help me with the values, then it will be better. So the value of log 2 is 0.3010 into 20. So it is going to be 6.02n only, and it must be remembered also, it is 6.02n minus log 3 is equals to 4.771 into 10, 0.4771 into 10, it is minus 4.77. So it is the decibel value, and what is given in the question is the signal to quantization ratio of at least 90 dB. We have to maintain the SNR either 90 dB or more than that. Therefore, if you equate given SNR dB, that is 6.02n minus 4.77, it must be greater than 90 dB. Therefore, you can write that 6.02n, it must be greater than 94.77. Therefore, n must be greater than 94.77 divided by 6.02. And if you calculate it, 94.77 divided by 6.02, so it is coming out to be 15.74. So n must be greater than 15.74. And as n is an integer, therefore n must be equals to 16. Minimum value of n is what? N is equals to 16. So the value of n, that is b plus 1 quantizer. So b plus 1 value is what? It is equals to 16. Accordingly, option D is correct for this given question. I hope you can understand the solution. Moving to the next question, the noise variance sigma E square at the output Hz with respect to input will be nearly. See, it is not 100% appropriate question, I think, but still what we can understand from this given question, it is given the noise variance sigma E square at output of this filter. If we are having a system which is having Z transform given as H of Z is equals to 0.5 Z upon Z minus 0.6. So we have to compare input and output variances. That is, if you consider a zero mean value of input, then output will also have mean zero. So you have to compare whatever, if we are applying any power in input, then if we calculate the power in output, then comparing those two powers, we have to say, or we have to identify that output variance or output power of the given system will be 40% or 50% or 60 or 70% of the input power. So if you see here, it is the standard result, that is, if the function is a to the power n un, then it has a Z transform which is given as, either you can write 1 upon 1 minus AZ inverse, or equivalently it can be written as Z upon Z minus A. So it is nothing but same value, that is 0. So if you are having H of Z as 0.5 into, you can write it like this, into Z upon Z minus 0.6. So if you see here, it is of the form Z upon Z minus A. It is a constant value. So you can find that input in time domain, the impulse response of the given filter is equals to 0.5 times Z upon Z minus A will have inverse transform, that is a to the power n un, therefore it will be 0.6 to the power n un. So it is impulse response of the given system, that is 1 by 2 times 0.6 to the power n un. So if you are having this system, then for comparing input and output noise power or variances, or you can say energies, if you take a function in the input and accordingly if you are having impulse response, then you can calculate the output. So then you can compare input and output values. So let's say for simplicity, let this x of n, if we take x of n as del of n, if this system is having impulse response hn, then output is going to be what? Y of n will be nothing but x of n convolved with hn. If you have taken x1 to be del n, then output will be del n into hn. And you know that convolution of any function with impulse function results in itself. Therefore, the output yn in this case will be input impulse function hn itself. So if you take, and therefore we call it as impulse response. Therefore, that is, if the input is an impulse function, then output is going to be the response for this impulse, that is known as impulse response. So if we take, let input xn is del n, then in this case, then output yn is equals to hn only. So if you compare energies of these two functions to compare whether it is decreasing by 40%, 50%, 60 or 70%, then you can understand, that is, if input xn is del n, then energy of input, energy is given as summation from n equals to minus infinity to plus infinity magnitude of x of n whole square. So in this case it will be given as minus infinity to plus infinity. Magnitude of del of n whole square will be equals to del n into del n. You can write del n square as del n into del n, and you know that for this result, if you use the product property or shifting property of impulse function, then x of n into del n integrated summation from minus infinity to plus infinity will result in del of 0 into del of n, and del of 0 is 1. Therefore, for this value only, I am just taking this value, it is equals to going to be del of 0 into del n, that is equals to del n only. So del n into del n is equals to del n only, del n square equals to del n only, and therefore this overall result will be equals to summation from n equals to minus infinity to plus infinity del n only, and del n is having only one value at n equals to 0, all other values are 0, therefore 0 plus 0 plus 0 plus 1 plus 0 plus 0 plus 0 will result into 1 itself. So the value is 1, and you must be knowing that the energy of discrete time impulse function is equals to 1, its power equals to 0. And if you will be taking a continuous time impulse function, then that will be an unbounded signal, therefore that must be an neither energy nor power signal. So input energy we have obtained as 1. If you find the output energy, so output yn is equals to hn, that is equals to 0.5 times 0.6 to the power nun. In the last class, when we were discussing PYQs of signals and systems, then we have already seen that if a function is of the form a to the power nun, then its energy value is equals to, for any function a to the power nun, if you can remember, its area, we have written two values, area and energy. Area value is 1 upon 1 minus a, and energy value is 1 upon 1 minus a square. So you can directly calculate as well for this function only, not multiplied with 0.5. For 0.6 to the power nun, for this part only, energy is equals to 1 upon 1 minus a square, that is 0.6 whole square. So it will be 0.36, that is equals to 1 upon 1 minus 0.36 is 0.64. So for this part only, energy will be 1 upon 0.64. So if you have to find energy multiplied by this, so if you are multiplying any constant, then energy will get multiplied square of this value. So for this overall function, the energy will be 0.5 whole square into energy of this function, that is 1 upon 0.64. So the overall energy of this function is going to be 0.25 upon 0.64. But if you have to evaluate by step by step, then you can find output energy. Output energy is equals to summation n equals to minus infinity to plus infinity h of n magnitude whole square. If you see here, h of n is having un, that is, it is present only from 0 to infinity. So you can take this limit as from n equals to 0 to infinity. At the place of h of n whole square, if you are going to square this value, un square will have a value un only. Therefore, you are taking 0 from 0 to infinity. For this 0.5, if you square it, so it will be 0.25 into, if you square 0.6 to the power n. So either you can write it like 0.6 to the power 2n, or you can write 0.36 to the power n. You have squared 0.6, so it will get 0.36 and it will have a power n. So now you are going to get 0.25, you can take it as outside as it is constant, and the value of summation from n equals to 0 to infinity 0.36 to the power n. So it is 0 to infinity a to the power n. If this a value is less than 1, then it is a standard summation which is having a value 0 to infinity a to the power n is 1 upon 1 minus a. So it is going to be 0.25 into 1 upon 1 minus a, and at the place of a you are having 0.36, so it is going to be 0.25 divided by 0.64. That is what I was talking earlier, that is, if you have to find energy of this part only, then it is going to be 1 upon 0.64, and if you are going to multiply 0.5, a constant value with this function, then the overall energy of this function is equals to 0.5 whole square into energy of this function, that is 0.25 upon 0.64. So now if you compare energies of input and output, so what you are going to observe is input energy is 1, output energy is what? 0.25 upon 0.64, that is 25 upon 64. If you calculate it, it is going to be nearly equals to 0.39. So if you see here, the output energy is 0.39, or you can say 39%, almost equals to 39% of the input energy. So output energy is nearly 40% of input energy. So based on this result, you can say that output power will also be almost 40% of input power, and accordingly the sigma E square, if you are comparing, the variance of output will be 40% to the variance of input. It can be said, but it is not exact result. But still, if you have to select one of the options, then option A is correct. That is, output variance is nearly 40% of the input variance. And accordingly, option A is correct for this given question. Moving to the next question, it is, in modulation system, the energy per bit to noise power density ratio EB upon N naught is. See, energy per bit is given as, it is power into time. And this power is nothing but carrier power. This carrier power is mentioned as C. So it is C. It is nothing but this carrier power. So it is equals to C into T, bit duration. It is C into TB. So EB, we have to find the ratio EB upon N naught. So EB is equals to C times TB. Now this N naught is power spectral density, where N is noise power of thermal, or we can say thermal noise power. So N is equals to thermal noise power. So thermal noise power is equals to what? KTB. That is equals to KT, that is eta. It is only given as N naught. So it can be written as N naught into B. It is power spectral density eta, that is equals to N naught, represented in this case by N naught. So if you find N naught, then N naught is going to be, N naught is equals to B upon N. N naught is equals to N upon B. So N naught equals to B by N, okay? N naught is equals to N upon B, okay? N upon B. N naught is equals to N upon B. So if we have to find EB upon N naught, so EB upon N naught, it can be written as EB is C into TB upon N naught is N upon B. So this B will move to the numerator, and it will be C into B divided by N into, see this here, it is 1 upon TB, it can be written as 1 upon FB as well, and 1 upon FB is nothing but TB. This TB can be written as 1 upon FB, that is FB. So C into B upon N into FB. C into B upon N into FB. Accordingly, this option C is correct for the given question. C upon N into B upon FB. Therefore, option C is correct for this given question. आपने लिखा रवि कि इसमें डेल एन ही क्यों लिया, ठीक है? तो यही मैंने कहा कि ऐसा इसमें कुछ भी और मेंशन नहीं किया गया था कि हम इसमें कंपेयर कर सकते थे। ऐसा कोई ज़रूरी नहीं था कि हम डेल एन ही लेते, ठीक है? आप अगर मान लीजिए इस क्वेश्चन में डेल एन नहीं लेते, ठीक है, यहाँ पर आप दूसरा कुछ लेकर चलना चाहते, कोई प्रॉब्लम नहीं है। अगर आप इसी केस में, अगर यहाँ पर आप ऐसा ले लेते, केस 2, लेट्स से xn इज 0.2 टू द पावर n given, ऐसा भी ले सकते हैं। ये कोई इनपुट हमने ले लिया, ठीक है। इस केस में इनपुट एनर्जी कितनी है? अगेन इट इज द फंक्शन विच इज a to the power n un, and for a to the power n un function, energy is 1 upon 1 minus a square. That is 1 upon 1 minus this. If it is a, then the value of a square is 0.04. So the value will be 1 upon 0.96, whatever value it is having. So you can find input energy. Then output will be what? Output will be xn convolved with hn. That is, and in this case, if you have to find the convolution in time domain, then it will be taking much more time. Therefore, what you can find is, find the output in z domain. So it will be x of z into h of z. X of z will be a to the power n un, will have a transform z upon z minus a, into h of z is given to be 0.5 times z upon z minus 0.6. So by taking partial fraction and then simplifying for y of n, you can find y of n. So you will be having some y of n signal. So if you find y of n signal, then again you can take the energy of this yn signal. Then if you are going to compare these two energies, then again you will be finding that output energy is 40% times the input energy. So to get the result quickly, or you can say to move to reach the result quickly, we have taken energy signal, input signal to be done. Otherwise, any other signal will tend to give you the same result, that is energy, output energy is going to be 40% times the input energy. Is it clear? Okay, good. Good. So now we are moving to the next question. It is assumed that the quantization error is a sequence of random variable where the statistics do not change with time. See, there are some statements given for the quantization error. This quantization error is assumed to be a stationary random process. This quantization error, if you are going to take it as a sequence of random variable, so it is a stationary random process, and for a stationary random process the statistics do not change with time is the correct option. If you see, then this statement is correct, as we are considering quantization, whenever we are considering quantization error as sequence of random variables, then these values are considered as stationary random process. Stationary random process. Therefore, statistics do not change with time is the correct statement. Again, it is a sequence of uncorrelated random variables is absolutely correct. That is, if you are going to take quantization error as a sequence of random variables, then expected value of, if you see that expectation of x of m, x of n, then it is going to be 0. Expected value of x of m into x of n, if m is not equals to n, then it is equals to 0. M is not equals to n, then it is equals to 0. So these values are uncorrelated to each other. So this first statement is correct, second statement is also correct. Now if you read the third statement, it is uncorrelated with the quantizer input x of n. It is again correct option, that is it is uncorrelated, that is if you are going to take, that is x of n, and for quantization noise, if you write here for noise, let's say if you are writing n, so n of n is equals to 0, and x of n into n of m is also equals to 0. So it is not going to be correlated with the input, so it is also 0. Therefore this statement is also correct. It is uncorrelated with the quantizer input xn. So xn into n of n is going to be 0. Expected value of xn and n is going to be 0. The probability density function is uniformly distributed over the range of values of quantization error. This is absolutely correct. You know that if you are having two levels and the total step size is s, if it is s, then the quantization noise is uniformly distributed between this s by 2, it is s by 2. So quantization noise power is uniformly distributed between minus s by 2 to plus s by 2. It is uniformly distributed between minus s by 2 to plus s by 2. That is, let's say if the value is exactly here, then there will be no error. If the value is here and you are taking the value on this level, then you are taking no error. But let's say the actual value is at this point and you are going to take the value at this. So maximum error, quantization noise, maximum error may be plus s by 2 or minimum error may be minus s by 2. So minus to plus s by 2, quantization noise power is uniformly distributed. Probability density function is uniformly distributed between minus s by 2 and plus s by 2. So all these statements are correct. Therefore the option 1, 2, 3 and 4, and accordingly this D option is correct for the given question. Next, if you see, which one of the following is not a property of Gaussian random process? Now we have to check statements for Gaussian random process. A Gaussian process is completely described by its mean and autocorrelation. It is absolutely correct. बिकॉज इट इज़ अ मल्टीवेरिएट गॉसियन। अगर आप देखेंगे तो गॉसियन रैंडम प्रोसेस के लिए सिर्फ अगर आपको उसके बारे में, इसलिए आप क्या, जब भी गॉसियन रैंडम प्रोसेस को आप डिफाइन करते हैं तो सिर्फ मीन और वेरिएंस से ही डिफाइन करते हैं उसको। इतना उसके लिए जानना आपका, मीन और ऑटो कोरिलेशन से आप पूरे किसी भी गॉसियन फंक्शन के लिए गॉसियन रैंडम प्रोसेस को बिल्कुल डिस्क्राइब कर सकते हैं। तो ये ऑप्शन आपका करेक्ट है। नेक्स्ट ऑप्शन इज, इफ अ गॉसियन प्रोसेस इज वाइड सेंस स्टेशनरी then it is stationary in the strict sense too. See, actual statement is, if we are not considering particularly the Gaussian, then if a random process is strict sense stationary, then it will be wide sense stationary as well. But it is not necessarily true. That is, if a function is if a random process is wide sense stationary, then it may or may not be strictly stationary random process. But in case of Gaussian, what you know is, if the Gaussian random process is wide sense stationary, then there is no need to check. It will definitely be strictly stationary as well. So for Gaussian, it is correct statement. This statement is correct for Gaussian, not for every random process. For Gaussian, this statement is also correct. Now, third option is, what we have to take here, which one of the following is not a property? Not a property, we have to find out. So option A is a correct statement about Gaussian random process. Option B is also a correct statement about the Gaussian random process. Next, if a Gaussian process is given as input to an LTI system, the output process is also Gaussian. See, again we can follow the central limit theorem. What central limit theorem states is, if you are going to take repeated convolution of different probability density function, then ultimately you will be reaching a Gaussian PDF. And if you are going to convolve any other PDF with Gaussian, then the resultant will always be a Gaussian function as only. So whatever is the impulse response h of t for this LTI system, whatever is the impulse response, if you are convolving any Gaussian random process, let's say it is g of t, so gt into st will always result into a Gaussian function. अगर आप किसी भी probability density function, मतलब किसी भी शेप को Gaussian शेप के साथ कन्वॉल्व करेंगे तो रिजल्टेंट हमेशा क्या होगा? Gaussian ही होगा। अब अगर आप एक Gaussian PDF को किसी LTI सिस्टम से पास कर रहे हैं तो आउटपुट हमारे पास जो PDF आएगा वो कैसा आएगा? इन दोनों का कॉन्वोल्यूशन आएगा। तो एच ऑफ टी चाहे किसी भी शेप का हो, उसका गॉसियन के साथ कॉन्वोल्यूशन आपको क्या मिलेगा? हमेशा गॉसियन ही मिलेगा। ठीक है, तो इसलिए हमारा ये भी जो रिजल्ट है, ये भी स्टेटमेंट बिल्कुल करेक्ट है। आप कह सकते हैं इसमें सेंट्रल लिमिट थ्योरम, दैट इज convolution of Gaussian with any other equals to Gaussian. It is not central limit theorem. Central limit theorem states that repeated convolution of different PDFs will ultimately result into a Gaussian function. And once it is a Gaussian function, then convolution of a Gaussian PDF with any other PDF will always result into a Gaussian function only. So C option is also not a property, is not correct. It is a property of Gaussian process. So option C we cannot take. Next, if you see, we are left only with this option, so it must be the correct one. If two processes which are jointly Gaussian are uncorrelated, then they are statistically dependent. See here, what this word is mentioned is dependent. If two processes which are uncorrelated, then they are dependent is absolutely wrong. It is absolutely wrong. In general, you cannot say that if two processes are uncorrelated, then it may or may not be dependent. But in case of Gaussian, if two processes are uncorrelated, then definitely they will be independent to each other. If in case of Gaussian, Gaussian processes if jointly uncorrelated, then definitely independent. They will be definitely independent. So this statement is not correct about the Gaussian process, and as we have to select the not property of Gaussian, therefore this D option will be selected as the correct one. So option D will be selected. Option D. I hope you can get the points. Next question is, the signal power and noise power measured at the input of an amplifier are 150 microwatt and 1.5 microwatt respectively. If the signal power at the output 1.5 watt and noise power at 50 milliwatt, what is the amplifier noise factor? See here, what we are having is, let's say it is an amplifier. So at input, what you are having is input signal power. It is given to be input signal power is noise power, signal power and noise power. So it is the signal power 150 microwatt, 150 microwatt, and input noise power. Noise power at input is given to be, that is equals to 1.5 microwatt, 1.5 microwatt. At output, the noise power and signal powers at output are given as, signal power is 1.5 watt, 1.5 watt, and noise power is 40 milliwatt. 40 milliwatt. Noise power at output is 40 milliwatt. So we have to find out the amplifier noise factor. So noise factor is input signal to noise power ratio of input signal to noise power ratio to the output signal to noise power ratio, SNR at output. You just have to evaluate this ratio, and accordingly SNR at input is, both the values are in microwatts, it will be 150 divided by 1.5 divided by, because both the units are same for input, but at output it is 1.5 watt divided by 40 milliwatt, which can be written as 40 into 10 to the power minus 3 watt. So it is 150 upon 1.5 is 100 divided by, it is going to be what? It will be this 10 to the power 3 you can take in numerator, so it will be 1500 divided by 40. So overall value what you are going to get is, one value will get cancelled, so it is 400 divided by 150, that is 40 upon 15, and 40 upon 15 is 2 times 2.66. So accordingly, the option A is correct for this question. Option A is 2.66 is correct. That is, whenever you have to find noise factor, then it is signal to noise ratio at input to the ratio with signal to noise ratio at output. So accordingly, option A is correct for this given question. Next, a receiver has noise power bandwidth of 12 kilohertz. What we are having is, B is 12 kilohertz. Resistor which matches with the receiver input impedance is conducted across the antenna terminals. What is the noise power contributed by this resistor in the receiver bandwidth? Take temperature as T is given to be 30 degree centigrade, that is converted to 273 plus 30, that is equals to 303 degree Kelvin. So if you see here, you have to find the noise power generated in the resistor. So noise power is equals to what? N equals to KTB. K is what? 1.38 into 10 to the power minus 23. absolute temperature is given to be T is 30 degrees centigrade, which is equals to 303 degree Kelvin, into bandwidth B is 12 into 10 to the power 3. So it is going to be what? If you multiply, then you are going to get 1.38 into 303 into 12 is equals to 5017.68 into 10 to the power minus 23, and plus 3 is minus 20. So if you are having all the options in 10 to the power minus 17, so you can write 5.017 into 10 to the power 3 into minus 20. 10 to the power minus 20 will result into 10 to the power minus 17, and accordingly if you see, option D is correct. So very good, Ravi, you are solving the options. Good. So moving to the next question, and the question is, an amplifier has a bandwidth of 4 megahertz. Again, you are given a bandwidth B is equals to 4 megahertz, that is 4 into 10 to the power 6, with 10 kilo ohm as the input resistance. Value of resistance R is given to be 10 kilo ohm, that is 10 into 10 to the power 3 ohms. What is the RMS noise voltage? RMS noise voltage, now we have to find V and RMS, that is equals to, we have already written, that is 4 kTBR. This value we have to obtain. K value is a constant that we already know. B and R as given, and we have to find it at room temperature. So T is 25 degrees centigrade, that is equals to 25 plus 273 Kelvin, that is equals to 298 Kelvin. So if you substitute all the values, then you are going to get 4 into K is 1.38 into 10 to the power minus 23. 4 K T is 298. T 4 KTB is 4 into 10 to the power 6 into R, that is 10 into 10 to the power 3. And you have to take square root of this. Now if you find the value, so it is going to be 4 into 1.38 into 298 into 4 is equals to 6579. 6579. We have I just have multiplied this value, this. Now total 10 to the power we are left with is, in positive we are having 6 plus 3 9 plus 1 10, total power 10, and in negative here it is minus 23. So we are having into 10 to the power minus 13. 6579, it is 6579.84 into 10 to the power minus 13. It can also be written as, if you have to take value minus 12, then you can write 657.98 into 10 to the power minus 12. Now if you are going to take square root of this, so square root of 10 to the power minus 12 will give you 10 to the power minus 6 into square root of this 657.98. Square root of this is equals to 25.65. 25.65. Accordingly, if you see, for 10 to the power minus 6, it may be written in microwatt. Therefore, the option C is correct for this given question, 25.65 microvolt. So accordingly, option C is correct. Very good, Ravi, your option is absolutely correct. So moving to the next question, an AM super heterodyne receiver with IF intermediate frequency of 455 kilohertz is tuned to the carrier frequency of 1000 kilohertz, the image frequency is. So it is the basic direct formula based question, that is image frequency. Image frequency is equals to signal frequency, that is it is actually equals to frequency of local oscillator plus 2IF, or you can directly write in terms of signal frequency. So it will be frequency of signal, desired signal, which is nothing but the tuned RF carrier. In this case, this signal frequency is equals to 1000 kilohertz, that is tuned RF carrier frequency, plus twice IF, twice of intermediate frequency, that is equals to 1000 and plus 2 into 455, it is standard value of intermediate frequency. So it is equals to, what is image frequency actually is, if you see here, what is this intermediate frequency? It is, if you design a super heterodyne receiver, then you put the value of intermediate frequency greater than FLO, local oscillator frequency, by 455 kilohertz. So if the difference of local oscillator frequency and signal frequency is, it must be maintained at 455 kilohertz. So if it is plus 45 kilohertz or minus 455 kilohertz, the audio amplifier is not going to discriminate between these two positive or negative frequencies. So the signal which is not the actual signal but having the same intermediate frequency will result in the form of a noise, which is not your desired signal, is a noise for you. Therefore that signal is known as image signal. So image signal frequency is equals to frequency of desired RF carrier plus twice of intermediate frequency, and it is going to be what, 1000 plus 2 into 455, that is 910, and plus 1000, it is going to be 1910 kilohertz, and accordingly option D is correct. Actually having some problem with ACM. Okay, यहाँ तक में किसी को कोई डाउट तो बता देंगे एक बार. Yes, option D is correct. Next, if the modulation index of an AM wave is changed, it is not charged, it must be changed. Changed from 0 to 1, the transmitted power. See, in case of AM, total transmitted power PT is what? It is simply PC times 1 plus M square by 2. You know that the total transmitted power is equals to PC plus PC into M square by 2, where PC is carrier power and PC into M square by 2 is total sideband power. So in full AM, there is carrier and both of the sidebands are present. So case 1, if you are changing modulation index from 0 to 1, so if M is equals to 0, then what is going to be the value of PT? It is equals to PC into 1 plus 0, that is equals to PC only. That is, if no modulation is present, then total transmitted power is carrier power itself. And if you are going to change the modulation index to 1 in next case, so in case 2, if you are going to take M equals to 1, so PT is equals to PC into 1 plus 1 by 2. 1 plus 1 square by 2, that is 1 by 2. So it is going to be 1.5 PC, that is equals to 1.5 PC. So as you see, the transmitted power has increased from PC to 1.5 PC. That is, it has increased by 50% of its earlier value. Therefore, option A is correct. That if you are going to increase modulation index from 0 to 1, then correspondingly the transmitted power in AM will be increasing by 50% of its initial value. Next, for an AM signal, the bandwidth is 10 kilohertz and the highest frequency component present is 705 kilohertz. The carrier frequency used for this AM signal is. So you know that in double sideband suppressed carrier or in the full AM, what frequencies are going to be present after modulation? So your baseband signal is translated to a your baseband signal, which is a low pass signal which is centered at 0 frequency, Now that signal will be centered at your carrier frequency. So if the carrier frequency is fc, then sideband frequencies, sideband frequencies is equals to fc plus minus fm. fc plus minus fm, that is, let's say if you are having this as your baseband signal, let's say it is your x of omega, let's say it is your x of omega with respect to omega or x of f, then after modulation what you are going to get as amplitude modulated waveform spectrum. So x am of omega, x am of omega is what? The same band which is from minus omega c to plus omega c. This same spectrum will be centered not at 0 now. Now this spectrum will be centered at a frequency which is equals to your carrier frequency omega c. So the highest frequency will be omega c plus omega and the lowest frequency will be omega c minus omega. And the difference between these two frequencies is known as your bandwidth. The similar spectrum will present on the negative for the negative frequencies as well. So at this side you will be having at centered at minus omega c, it will be minus omega c minus omega m and minus omega c plus omega. And if here the value is 1, then you know that the value is 1 by 2 here. So it is the spectrum because what you take as amplitude modulation, in amplitude modulation x am of t, x am of t is what? AC plus xt. You are going to change the amplitude of your carrier. Your carrier is Vc of t is your carrier, that is AC cos omega ct, AC cos omega ct, and you are going to change this amplitude of this carrier, that is AC, according to the intelligence of your baseband signal or transmitting signal, that is you have to transmit, that is AC plus xt. You are changing amplitude with respect to xt into cos omega ct. So now if you are going to take the Fourier transform, so if you are having full AM, then you will be having two impulses at these frequencies as well. So you are going to get it is AC cos omega ct and plus AC cos omega ct plus xt cos omega ct, xt cos omega ct. And if you are going to take it in frequency domain, so x am of omega, it is equals to, for AC cos omega ct, the transform will be AC into pi, because the transform of cos omega ct is pi times del of omega minus omega c, del of omega minus omega c plus del of omega plus omega c. And for this xt cos omega ct will have a transform, that is 1 upon 2 times x of omega minus omega c plus x of omega plus omega c. You must have done this in the basics of AM. Therefore in AM what you are having is, you are having two impulses at frequencies plus and minus omega c, this and this, these two impulses. All these impulses will have a strength AC into pi. So AC into pi is the strength of this impulse here also. And you will be having both the side bands, this same spectrum of x of omega, it is one shifted by omega c in positive direction and one in negative omega c in the left hand direction. So this baseband spectrum is now centered at plus and minus omega c. So maximum frequency component is omega c plus omega m. In radians per second if you see, then it is omega c plus omega m. In hertz if you will be seeing, then it will be fc plus fm. So maximum frequency component is equals to omega c plus omega radians per second or fc plus fm hertz. Bandwidth, similarly minimum frequency component, then it will be omega c minus omega m radians per second or fc minus fm hertz. And bandwidth is equals to maximum frequency minus minimum frequency, that is omega c plus omega m minus of omega c minus omega m So it is going to give you twice of omega m in radians per second, or similarly you can write twice of fm hertz. So these values are given to you. That is, bandwidth is 10 kilohertz. So what you are having is bandwidth, that is twice of fm. It is equals to 10 kilohertz. So what you can obtain from here is maximum frequency component of the baseband signal or modulating signal is fm is equals to 5 kilohertz. So first we have obtained fm is equals to 5 kilohertz. Next, what you have given is maximum frequency component present is 705 kilohertz. Maximum frequency component. These are given. Maximum frequency component. That should be fc plus fm. It is given to be 705 kilohertz. And you have asked to find carrier frequency. Therefore fc is equals to 705 kilohertz minus fm, and you have already obtained the value of fm, that is 5 kilohertz. Therefore 705 kilohertz minus 5 kilohertz will give you 700 kilohertz. So it is the value of carrier frequency, that is equals to 700 kilohertz, and accordingly option B is correct for this given question. I hope you can understand. Next, which one of the following desirable features are possessed by SSB in comparison to AM? See, in full AM, what you transmit is XAM of T. It is equals to total transmitted power. If you see, then in full AM, total transmitted power is PT into 1 plus m square by 2. That is PC. It is PC into 1 plus m square by 2, which is equals to PC plus PC into m square by 2. That is, it is carrier power. It is carrier power, and it is power in two sidebands. Power in two sidebands. So in full AM, you transmit carrier as well, which has no information. It is redundant to transmit, and you are transmitting both of the sidebands, while you are knowing that only one sideband is sufficient to represent a signal. Other sideband, you are just wasting your power and bandwidth. So in SSB, what you do is you suppress that carrier, total carrier power, and only one of the sidebands is transmitted. So in SSB, transmitted power is only one sideband is transmitted. So if two sidebands are having total power PC into m square by 2, so the total power in only one sideband it will be PC into m square by 4. This much power only need to transmit. So in case of SSB, you are suppressing, in case of SSB, carrier and one sideband is suppressed. One sideband is suppressed. Therefore, if you have not transmitted the carrier, you have saved carrier power, and we have not transmitted one of the sidebands as well. So you have saved one sideband power as well. Apart from this, you will be needing less bandwidth to transmit, because only one sideband is getting transmitted. If you are transmitting both of these sidebands, so you are having the need of bandwidth to be maximum frequency omega c plus omega minus minimum frequency omega c minus omega. If you will be transmitting only one of any of the sidebands, so the transmission bandwidth required will be omega m only, because it will be your minimum and it is your maximum frequency. So omega c plus omega m minus of omega c will result into omega. So in SSB, you are going to save bandwidth as well as power. So now if you read the statement, less power is required is correct statement. Bandwidth required is less is correct statement. Antenna size can be reduced is absolutely not correct, because there is no effect on the size of antenna if you are going to transmit either carrier only or you are not going to transmit carrier. Antenna size is independent of the transmission of either you are transmitting carrier, because size of antenna depends which signal you are going to transmit. The more value of higher for higher signals you will need lesser antenna size, but the maximum frequency component is same in case of DSB SC, SSB SC or in FM. So antenna size will be same, requirement will be same for both SSB and AM. So this statement is not correct. And lower frequency can be used. It is also not correct, because in SSB you are having same modulating signal, same carrier to generate SSB signal. So lower frequency can be used is not correct statement. So only 1 and 2 statements are correct, and accordingly option C is correct for this given question. Moving to the next question. In amplitude modulation, the modulation envelope has a peak value which is double the unmodulated carrier value. What is the value of modulation index? See, what you do in amplitude modulation, let's say it is your carrier. Let's say it is your carrier signal. So you are superimposing your baseband signal or modulating signal over this carrier. So if the baseband signal is having a shape like this, so you are going to get it as your envelope. So it is going to be the envelope of AM signal, and in this envelope you are having this kind of values. So it is your envelope of AM signal. So this envelope has the envelope varies. See, it is your amplitude of your carrier signal, it is AC. It is amplitude of modulating signal from this, if you see, it is value of AM. So this point, that is the peak value of envelope, is reaching to AC plus AM. AC plus AM, the peak value of envelope is what? AC plus AM. And the minimum value of envelope will be what? If it is AC and it is the amplitude of your baseband signal or modulating signal which is equals to AM, so this is getting decreased by AM. It is AM and this, it is also equals to AM. It is your amplitude, it is your modulating signal. So modulating signal is having an amplitude equals to AM. So the envelope will have a peak equals to AC plus AM, and it will have a negative minimum value that will be equals to AC minus AM. So if you see here, then this minimum value of this envelope will be AC minus AM. So what you can write here is envelope of AM varies from AC minus AM to AC plus AM. It means the peak value of envelope is what? Therefore, what you can write is peak value of envelope. Peak value of envelope is equals to AC plus AM. Now, what you are having in this question is peak value of envelope which is double the unmodulated carrier value. Given, if you have given that this peak value AC plus AM, it is equals to double the unmodulated carrier value, that is, it is equals to twice of AC. Unmodulated carrier has an amplitude AC, therefore this peak value of envelope is equals to twice that unmodulated carrier value, therefore AC plus AM is equals to twice of AC. Therefore from this equation what you can infer is AM is equals to AC only. Therefore AM is equals to AC. Now if you have to find the value of modulation index, therefore modulation index, and you know that modulation index M is equals to AM upon AC, that is equals to AC upon AC, that is equals to 1. Therefore modulation index is 1, or you can say 100%. Therefore option D is correct for this given question. Peak value of envelope, it should be AC plus AM, it is equals to twice of AC. It means AM is equals to AC, therefore the ratio of AM to AC, which is known as modulation index, will be 1. That is, depth of modulation is 100% in this case. Therefore option D is correct. Moving to the next question. Which of the one of the following is correct? The type of modulation used generally in the TV transmission for video and audio signals represent respectively are. So in TV transmission, you must be knowing that for video signal we use AM, which is not completely AM, it is VSB, and for audio signal we use FM. So if you see the correct option, we have to say for video and audio. So video, for video we use AM, and for audio we use AM. No, AM no, AM and FM, that is option D is correct. For video signal AM, and for audio signal in TV transmission we use FM. Normally the question comes that in TV transmission which of the modulation is used, then you have to select VSB, vestigial sideband modulation. Okay. Next question is, a DSB signal is generated using the carrier signal and modulating signal MT. What is the envelope detector output of this DSB SE signal? See, it is not, I can say it is not a correct question, because you never use envelope detector to detect DSB SE signal. Carrier must be present to detect envelope. But still, if you see, envelope is nothing but by envelope you need to extract your modulating signal. So for in this case, if you have to select the options, then definitely the option is magnitude of MT is the most closest option. So you'll be selecting this magnitude of MT, that is positive variations of MT signal will be detected. But it is the basic doubt, that is DSB, for to detect DSB SE we never use envelope detector in common cases. So but still, if you have to select the options, then magnitude of FT will be the most appropriate one. Okay, moving to the next option. The original spectrum of a message contains 100 Hz, 200 Hz frequency components. It is amplitude modulated by a carrier of 0.9 kHz. Which frequency components are contained in the amplitude modulated spectrum? So what we have already seen is frequency components present in, it is multitone AM, that is we are having more than one signal as modulating signal, which are used to modulate a particular carrier, that is of 0.9 kHz. So if you say it is your FM1 and it is your FM2 and it is your carrier frequency FC, then the frequency components will be present, will be carrier frequency will be present, that is there will be two impulses as at plus minus FC. So frequency FC will be present, frequencies FC plus minus FM1 will be present, and frequencies FC plus minus FM2 will be present. So what signal frequencies will be present is FC is 0.9 kHz, that is 900 Hz, FC 900 plus minus 100. So 900 plus 100 will give you 1000. 900 minus 100 will give you 800 Hz. And 900 plus minus 200 will give you 1100 Hz. And 900 minus 200 will give you 700 Hz. So 7, 8, 9, 10, 11. 7, 8, 9, 10 and 11 Hz. Therefore option C is correct. So for this question, option C is correct. Next, if two signals modulate the same carrier with different modulation depths of 0.3 and 0.9, the resulting modulating signal will. So it is the basic fact, that is overall modulation index MT equivalent, if you say M equivalent is equals to under root of M1 square plus M2 square plus M3 square. How many signals are there? You just have to take. So it is equals to M1 square, that is 0.3 whole square, that is 0.09, and plus M2 square, that is 0.9 whole square, that is 0.81. So it is going to be 0.9. And if you take square root of 0.9, then it will be resulting into it is going to be 0.9486. and accordingly if you select the nearest option, so it is nearly equals to 0.95 and have the resultant modulation index around 0.95 is correct option. So it is over modulated means modulation index is greater than 1, wrong. Resultant modulation index is 1, correct, not correct. Modulation index around 0.82, not correct. Most you can say closest to the exact option is 0.95, that is option D. So we'll be selecting this. Next, what is the power contained in SSB transmission when the carrier power is 1 kilowatt and the modulation index is 0.3? So what we have already seen is for SSB, total transmitted power is only one sideband power, that is equals to PC times M square by 4. It is the total transmitted power, that is we are transmitting just one sideband, we are suppressing the carrier and one sideband. So PT equals to PC times M square by 2. So carrier power is 1 kilohertz, that is 10 to the power 3 or 1000 watt, into M square, that is modulation index is 0.3, so M square will be 0.09 divided by 4. So it is going to be 90 by 4 and accordingly 22.5 watt is correct. That is option A is correct for this given question. Next, a carrier's amplitude modulated by 4 signals of frequency 10, 15, 20 and 25. What is the bandwidth of the modulating signal? See, bandwidth is what? Bandwidth is twice of FM. Twice of FM means the maximum frequency component of modulating signal. So if you are using 4 signals to modulate a particular carrier, then you just have to check which signal frequency is maximum among all of these frequencies. So 10, 15, 20 and 25 kilohertz. So bandwidth will be, let's say if it is FM1, it is FM2, it is FM3 and it is FM4. So the spread of this AM signal will be FC plus FM4. It will be the maximum frequency component of this spectrum minus FC minus FM4. It will be the maximum frequency component of the spectrum and it will be the minimum frequency component of the spectrum. Therefore, bandwidth is the difference of maximum to minimum frequencies. Therefore, the maximum bandwidth is going to be what? Twice FM4. It is nothing but twice of FM. So you just need to check which of the frequencies is maximum among the given frequencies or modulating signals. So you just have to take FM4 as FM and twice of FM will give you the bandwidth. So it is going to be twice of FM4. That is 2 into 25 kilohertz, that is equals to 50 kilohertz. Here we are taking FM4 as FM1 is less than FM2 is less than FM3 is less than FM4. So the maximum frequency is FM4, therefore the bandwidth is equals to twice of FM4, that is equals to nothing but 50 kilohertz. Okay, moving to the next question. The antenna current of an AM transmitter is 8 when only carrier is sent, but it increases to 8.93 when the carrier is modulated. So what you can see here, total transmitted power PT is total antenna current if after modulation, if you see, then it is equals to, it may be written as IT square into R. And we also know that this PT is nothing but PC into 1 plus M square by 2. PT is equals to 1 plus M square, PC into 1 plus M square by 2. Similarly, if it is modulated total power, if you see, PC is what? You can write it like IC square into R. That is carrier current whole square into R will give you carrier power. So if you put carrier power PC value is equals to IC square into R in this place, therefore PT, that is IT square into R, is equals to, at the place of PC if you put IC square into R into 1 plus M square by 2, then this R and R will get cancelled and therefore you will be finding that IT upon IC. that is current after modulation to ratio of current after modulation to the unmodulated carrier current. This ratio is going to be under root of 1 plus m square by 2. It is going to be 1 plus m square by 2. So here what you are having is IT, that is current after modulation, is 8.93. So 8.93 divided by current unmodulated carrier current is IC, that is equals to 8 ampere. So 8.93 upon 8, it is equals to under root of 1 plus m square. You need to calculate the percentage modulation, that is modulation index only. So it is 1 plus m square by 2. So if you calculate, if you take square root on both the sides, so square on both the sides, so 8.93 divided by 8 whole square. If you check 8.93 divided by 8, then it is 1.11, and if you take its square, then it is going to be 1.246. So 1.246 is equals to 1 plus m square by 2. I have taken a square on both the sides, so m square by 2 value will be what? 1.246 minus 1, that is equals to 0.246. Therefore m square is equals to 0.592. Therefore m is equals to square root of 0.592, which is going to be 0.592, and square root of this will give you 0.769. 0.769. Accordingly, it is nearest to 70%. So you can say that the nearest option is 70.14%. So option C will be correct in this case. So modulation index is equals to this. So you need to know this relation between modulated and unmodulated currents. So IT upon IC is square root of 1 plus m square by 2. Which one of the following is considered as an AM signal? Binary phase shift keying, differential phase shift keying, differential encoded PSK, quadrature PSK. Again, none of the options according to me is correct, because what in AM, what you do is, what is an AM signal? Amplitude varies, right? Phase and frequency remains constant. It is the basics of amplitude modulation. That is, if you are going to transmit a signal using amplitude modulation, then you are just going to modulate amplitude of the carrier according to the intelligence of your modulating signal, or you can say the baseband signal which you have to transmit. But the phase and frequency of the carrier must be what? Unchanged. So if you see in binary phase shift keying, then you are going to provide a phase shift of 0 degrees or 180 degrees. If you have to transmit 1, then you provide a phase shift of 180. If you have to transmit 0, then you normally provide a phase shift of 0 degrees to the carrier. So it means the phase is changing. So if the phase is changing, it is not equivalent to amplitude modulation. Similar things are there. Differential phase shift keying, again you see the change, change in phase in consecutive signals. Again, these are dependent on change in phases. Differential encoded PSK, again there, if it is written as PSK, means change in phase, here also change in phase occurs, change in phase, and this change in phase is encoded into other some values. And here it is, you are having quadrature PSK, again you are having 4 phase, 0 degrees, 90 degrees, 180 degrees and 270 degrees. So again you are having 4 different phases. So none of these are actually equivalent to amplitude modulation, but still if you have to consider as AM signal, then according to me you can take quadrature PSK, but still none of the option is absolutely correct. None is absolutely correct. None of the options are absolutely correct. So you can skip this question as well. No need to go with the solution of this question. Now an AM modulator has output 20 cos 300 pi t plus 6 cos 320 pi t plus 6 cos 280 pi t. Then what is the modulation index of wave? See, let's say your carrier signal is Vc of t, that is AC cos omega ct, and you have to transmit a signal x of t, that is equals to AM cos omega mt. Then what is the expression for x AM of t? X AM of t is AC plus xt. AC plus xt. At the place of xt, what you are having is AM cos omega mt. So it is AC plus xt into cos of omega ct. If you take AC common, so it will be 1 plus AM upon AC will be m into cos omega mt into cos of omega ct. Here is m is AM upon AC, that is equals to modulation index. M is what? AM upon AC, that is modulation index. So if you open this, then you are going to get AC cos omega ct plus m into AC cos omega ct into cos omega mt. And if you solve this by using cos A into cos B, then you are going to get AC cos omega ct and plus MAC by 2 into cos of omega c minus omega mt and plus cos of omega c plus omega mt. So if you see here, then you are going to get three signals, that is AC cos omega ct, first is the carrier, and these are two sidebands, and both the sidebands are having amplitude equals to MAC by 2. It is lower sideband omega c minus omega mt, and it is MAC by 2, it is upper sideband, which is having a frequency omega c plus omega. So it is given in the problem. It is your AC cos omega ct. It is, if it is 320 and it is 280, means it is lower frequency. So it is MAC by 2 cos of omega c minus omega mt, and it is MAC by 2 cos of omega c plus omega mt. So you just need to calculate the value of modulation index. So from this part, what you can understand is AC is equals to 20 cos t, that is 20 cos 300 pi t. So if you compare, that is if it is S of t equals to 20 cos 300 pi t, S of t is 20 cos 300 pi t plus 6 cos 320 and 280, 320 pi t plus 6 cos 280 pi t. So what, by comparing with the standard equation, and comparing with standard equation, AC is 20, MAC by 2 is 6, omega c is 300 pi radians per second, omega c minus omega m is 280 pi radians per second, omega c plus omega m is 320 pi radians per second. It means omega m is equal to 20 pi radians per second. This everything you can understand by comparing the given equation with the standard equation. So what you have to calculate is to find value of modulation index. So if you see here, if you put directly AC value, so m into AC is 20 by 2 is equals to 6. So it is 10. 20 by 2 is 10. So 10 into m is equals to 6. Therefore, m is equals to 6 by 10, that is equals to 0.6. So it is asked in the question. Otherwise, it may also be asked in the question. So if you have to find the value of modulation index, then m equals to 0.6. And accordingly, option D is correct for the given question. I hope you can get the solution. So you are having any doubt, then you can comment it in the comment section. Yes. Very good, TD. So the next question is, for which one of the following modulating signal the original message up to a scaling factor can be recovered using envelope detection? So to use envelope detector, modulation index must be less than 1. Means modulation index cannot be greater than 1, as the envelope will be distorted. So you just have to calculate for which of the cases modulation index is less than 1. So if you see these two cases, then these are DSB-SE signals, and for DSB-SE we don't use envelope detection. These two can be considered as full M, and for these two we will be using envelope detector. So if you compare this as AC cos omega CT plus M AC cos, so if you see here, if it is in this question, AC is 20, and if you compare, then you can say M into AC is equals to 30. It means M is equals to 30 by 20, that is 1.5, which is greater than 1. Therefore, we cannot use envelope detection to detect the signal from this. So this A option is not correct. If you see here, then AC is 20. See, actually it is not M into AC. But if you have to select the options, then you'll have to consider it as M into AC only. Then only you can find the options. So M here you are having M into AC is equals to 16, and therefore M equals to 16 upon AC, that is equals to 20, that is 4 by 5, that is equals to 0.8, which is less than 1. So it can be used, that is envelope detector can be used to detect AM signal from this modulated signal. Therefore option B is correct for this question. So for this question, if you have to select one, then option B will be selected. Okay, next question. In double sideband suppressed carrier modulation, the modulated wave undergoes phase reversal whenever. So you know that when you need DSB, when you see the waveform of DSB, then modulated wave undergoes the reversal whenever. So what is the expression for DSB-SC signal? X DSB-SC of T, it is equals to MT into cos omega CT. So when your modulating signal goes phase reversal, when this modulating signal is changing from positive to negative or negative to positive, that is when modulating signal crosses 0, then the overall DSB-SC signal will be having a phase reversal, and therefore this option C is correct for this given question. So whenever we will be discussing DSB in detail in the theory lectures, then I'll be discussing in more detail than why it is happening so. But for the time being, you just can take this as a fact. Then whenever the modulating signal crosses the 0 value, that is either it is changing from positive to negative or negative to positive, then the overall DSB-SC spectrum will have a phase change, that is phase reversal of 180 degrees. Next, bandwidth occupied by 100 megahertz carrier AM modulated by signal frequency of 10 kilohertz. Again, it is directly a formula based question. If AM modulated by signal frequency of 10 kilohertz, that is if you are having FM is equals to 10 kilohertz, then carrier frequency has no effect on the bandwidth. It is just the center frequency of the overall modulated signal. So the bandwidth of modulated signal depends on the signal frequency, that is modulating signal frequency or baseband signal frequency. And if it is FM, that is equals to 10 kilohertz, then bandwidth is nothing but twice of FM, that is equals to 20 kilohertz. And accordingly option B is correct. So the option B is correct for this given question. Next, if you see, RF carrier 10 kilovolt at 1 megahertz is amplitude modulated and modulation index is 0.6. Peak voltage of the signal is. Again, if the modulating in the modulation index is given M, which is nothing but AM upon AC, and if it is equals to 0.6, then you have to find the peak voltage of the signal. So if the carrier 10 kilovolt at 1 megahertz, that is, it is given to be the amplitude of carrier. So if AC is given, then AM is equals to M into AC, that is equals to 0.6 into 10 into 10 to the power 3, that is equals to what? 6 kilovolt. So the option C is correct for the given question, that is 10 into 0.6 will be 6 and to 10 to the power 3, that is 6 kilovolt, that is option C is correct. Next, a 1000 watt carrier is amplitude modulated and has a sideband power of 300 watt. The depth of modulation is, again what we have already discussed is, in AM total transmitted power is PC into 1 plus M square by 2, which can be separated as PC plus PC into M square by 2, and you have said that it is your carrier power and it is sideband power, which is power in two sidebands. So here it is given as sideband power of 300 watt means PC into carrier power is 1000 watt. So what you are having is PC into M square by 2. Sideband power is equals to 300 watt. And you are also having the value of PC as 1000 watt. So 1000 into M square by 2 is equals to 300, or you can see that it is 500 M square. So M square is equals to 300 by 500. Therefore M is equals to under root of 3 by 5. Is it right? It is 500. So M square is equals to 300 upon 500. Therefore M equals to under root of 3 upon 5, that is under root of 0.6. And under root of 0.6 will give you 0.6. Square root of 0.6 is 0.774. That is 0.774, and the nearest option is 0.775. So option C is correct for this question. Next, a 100 volt carrier peak changes from 160 volt to 40 volt by a modulating signal. The modulation factor is. So we have already seen that envelope of AM changes from, it is your AC plus AM, and this 40 is AC minus AM. So if you have to find the modulation factor, that is modulation index M, the modulation index M is AM upon AC. So you are having two equations. 100 volt carrier, that is, it is your AC. So if AC is equals to 100, AC plus AM is equals to 160, it means that AM is equals to 60. So you just have calculated values of AC and AM either by this or by using this also. It may be case that if this value would not be present in the question, then you will have to find the modulation index, then it will be AC minus AM upon AC plus AM. But if in this case you are already having the value of AC as well, so you can calculate the values of AM considering it as AC plus AM, so you have obtained AM equals to 60. So if AM is 60 and AC is 100, therefore modulation index is 60 upon 100, that is equals to 3 by 5, that is equals to what? 0.6, and accordingly option C is correct. You can find this value as 40 by 160 as well, so it will be AM minus AC upon AC plus AM. but no need to calculate using that. You just have to find out the values of AM upon AC, and that's why we have obtained the value of AM modulation index to be 0.6. Moving to the next question, the transmission power efficiency of a tone modulated signal with modulation index of 0.5 is nearly. See, modulation efficiency eta is equals to total useful power upon total transmitted power. Total transmitted power. If we are considering AM signal, then total useful power is power in sidebands upon total transmitted power is transmitted power. Sideband power is what? PC into m square by 2. We have already seen that transmitted in total transmitted power, PC into m square by 2 represents the sideband power, whereas PT, total transmitted power, is PC into 1 plus m square by 2. So it is total transmitted power is PC into 1 plus m square by 2. If you see, PC and PC will get cancelled, and you are having m square by 2 divided by, here you are having 2 plus m square by 2. So the efficiency eta, and if you are calculating it in percent, so it will be into 100%. So that is going to be 2 upon, that is m square upon 2 plus m square into 100%. So it is going to be the value of efficiency in case of full AM. And likewise, you can calculate the efficiencies for double sideband suppressed carrier or for single sideband suppressed carrier. The values of total transmitted carrier will be changed. So n equals to m square upon 2 plus m square, and you are having m value is equals to 0.5. So it is going to be m square, that is 0.25 divided by 2 plus m square into 100%. That is going to be 0.25 divided by 2.25 into 100%. And that is equals to 1 by 9 into 100%. That is 100 by 9, and that is equals to 11.1%. And accordingly, option B is correct. I hope all of you have understood this. 0.775 is correct for the previous one, Ravi. Absolutely correct. For this question also, you have given the correct option, 11.12%. Very good. So, amplitude modulated double sideband carrier wave, a peak unmodulated carrier voltage VC, a load resistance R, and a modulation efficiency, total power of modulated wave. See, today I am just leaving this session on this note only. We have solved 41 questions in this session, and in next two sessions we'll be covering all the ESE questions that has came in the electrical engineering subject, electrical engineering branch. So in the next session we'll be covering AM and FM completely, and in the last session we'll be discussing from bandpass data techniques and from miscellaneous topics of communication. So there will be 3 sessions of PYQs for this subject, communication systems, and you can आपसे ये मैं कहना चाहूँगा कि बिल्कुल आप लोग कमेंट सेक्शन में बताइएगा कि आप लोग सॉल्यूशंस को समझ पा रहे हैं या नहीं, सॉल्यूशंस को और डिस्कस करना है या फिर शॉर्ट रखना है, क्योंकि देखिए अभी 3 आवर्स ऑलमोस्ट ये सेशन हो गया, 3 आवर्स का सेशन हो गया। इसमें कितने क्वेश्चंस कर पाए हम लोग? 41 क्वेश्चंस। यहाँ पर मैंने आपके लिए 60 क्वेश्चंस ऑलमोस्ट इसमें रखे थे, तो थोड़ा सा यहाँ पर इसी के साथ भी प्रॉब्लम हो रही है, और वैसे भी 3 आवर्स से ज़्यादा सेशन मैं भी रखना भी नहीं चाहता हूँ। तो ठीक है, आज हम सेशन यहीं तक रखते हैं। 41 क्वेश्चंस आज हमने किए, और कमेंट सेक्शन में आप लोग बताइएगा जो भी आपकी रिक्वायरमेंट है। जैसे आज एक रिक्वायरमेंट हमें मिली कि हम चाहते हैं कि पूरे थ्योरी लेक्चर्स यहाँ पर अपलोड किए जाएँ, तो ठीक है, उसके लिए भी हम देखेंगे। लेकिन मैंने आपसे बोला कि जब हमारी स्ट्रेंथ इतनी होगी कि मुझे भी लगे पढ़ाने में कि हाँ यहाँ पर स्टूडेंट्स आ रहे हैं, तो फिर हम करेंगे उन सेशंस को। लेकिन अभी उसके लिए मैं आपको कुछ नहीं कह सकता। लेकिन आप लोग ये सेशंस करते रहिए, अपने प्रैक्टिस बनाए रखिए, और जहाँ भी आपको ESE से रिलेटेड सिग्नल्स में या कम्युनिकेशन में या कंट्रोल में किसी भी सब्जेक्ट में जो कि कॉमन टू ESE एंड EE है, क्योंकि मैं ESE ब्रांच मतलब EC ब्रांच का हूँ, तो जितने भी कॉमन सब्जेक्ट्स हैं उन सभी में आप मुझसे डिस्कस कर सकते हैं अपने डाउट्स को। ठीक है, तो फिर इस सेशन को आज हम यहीं तक रखेंगे। और दिस इज़ नॉट इन ESE, नहीं बिल्कुल, देखिए कम्युनिकेशन सिस्टम तो ESE और EE दोनों में ही है। अब यहाँ जो क्वेश्चंस लिए मैंने ये ESE के EE और EC दोनों से ही मिलाकर है, लेकिन मेनली ये EE वाले जो क्वेश्चन है वो ज़्यादा यहाँ पर आपको लिए गए। तो ऐसा नहीं है कि ये ESE के लिए EC के लिए इंपॉर्टेंट नहीं है, EC के लिए इक्वली इंपॉर्टेंट है, क्योंकि सब्जेक्ट तो दोनों ही जगह आपका सेम है। एम्पलीट्यूड मॉड्यूलेशन यहाँ भी, एम्पलीट्यूड मॉड्यूलेशन वहाँ भी है। तो बिल्कुल ESE के लिए ऐसा नहीं सोचना कि EC के लिए सेशन नहीं है, EE के लिए नहीं है, दोनों ही ब्रांचेस के लिए इक्वली इंपॉर्टेंट सेशन। ठीक है, तो चलिए फिर आज का सेशन हम यहाँ पर एंड करेंगे, और जो भी आपके डाउट्स हों कमेंट सेक्शन में बताइएगा, फिर नेक्स्ट सेशन में हम उसको कंप्लीट करेंगे। थैंक यू सो मच, ऑल द बेस्ट, टेक केयर, बाय, थैंक यू।